Welcome to the CMU SEI Research Review 2020.
Welcome back to day 3 of the 2020 CMU SEI Research Review. Sure, I'm glad that you're back after hopefully a day off for Veterans Day yesterday. So we didn't do the session yesterday based on the federal holiday, and hopefully all of you made it back in with no problem clicking on the links. So again, I'm Tom Longstaff. I'm the CTO of the Software Engineering Institute here. And just as a reminder, the SEI is a federally funded research and development center at Carnegie Mellon University focused on software engineering, cyber, and AI engineering. Back on Tuesday, you heard from many of our researchers focused in on cyber. The work represented that we've been presenting is our fundamental research portfolio, really along that path of doing the fundamental research into producing tools and techniques, and finally into real impactful research for the DoD and the US government generally. Today's objective is maintaining software development and acquisition, basically formalizing our development, integration, and use of models to advance software acquisition and improve designed-in resilience. Our master of ceremonies today is Jeff Bowling, and I know you'll really enjoy his framing of the day. We really have a terrific lineup today, starting with a panel of real visionaries from government, industry, and academia, not to be missed. So please stay with us and hear from some of the folks that you've seen in the news, that you've seen around, that are really framing what it is that we are doing. At the end of today, we'll have our second poster session, and I hope you enjoyed the first one on day 1. We're going to have another poster session at the end of the day today where you can actually have that personal one-on-one interaction with our PIs that you've heard from. And we'll have the details on that. They'll be up between sessions and you'll be able to see all the links on how to join from there. I will see you at the end of the day again today to reframe and capitalize on what happened. So now over to Jeff to start day 3. Thanks.
Hello, everyone, and welcome to day 3 of the Software Engineering Institute's Research Review. The theme for today is enabling DoD to produce systems that are agile and responsive to its mission. It's an exciting time, I think it's a really exciting time for DoD software. There's been a lot going on at the Department of Defense and in the services with things like rolling out large enterprise service offerings for DevSecOps. Really, a lot of progress has been made streamlining the authority to operate process and bringing in security guidelines for modern technologies like containers and Kubernetes. We've got a lot of really interesting workforce development things coming down the pipe too. We also, everybody's probably aware of the new adaptive acquisition framework, which from my perspective, actually one of the best parts of that is the new software acquisition pathway that really encourages use of reusing enterprise services, getting close to the customer, delivering capability incrementally on short timelines. So again, really an exciting time for DoD software. So today, first I want to say, if you have any questions or comments or need anything sort of resources, there's an email address here on this opening slide. It's info@sei.cmu.edu. Please send anything there, and we'll make sure that the right person gets back to you. So to kick today off at 11:30, we've got an amazing group of panel members led by, sorry about that. We've got an amazing group of panel members. Ms. Anita Carlton, who's the director of our Software Solutions Division, she's going to lead a group of panelists in discussions, basically asking them how do they envision software engineering shaping the future, and what is the future vision. So if you look at the panel members here, it's an amazingly distinguished group. Mr. Tim Dare, he's the software lead in DoD in research and engineering. Dr. Michael McQuaid is the Vice President of Research at Carnegie Mellon, which is SEI's home. Dr. Deborah Frinke from Oak Ridge National Laboratory is here. Dr. Vince Cerf is on the panel as well. He's a chief internet evangelist. Many people refer to him as the father of the internet, the godfather of the internet, something like that. Also, we're pleased to have Mr. Nand Mulchandani. He's the Chief Technology Officer at the Joint Artificial Intelligence Center in DoD under the Chief Information Officer. Mr. John Roberts also on the panel. He is Anita's deputy and been helping us lead an interesting study called the National Agenda for Software Engineering. Dr. William Shirless, who is a professor at Carnegie Mellon, but is currently at DARPA heading the Information Innovation Office at DARPA. And then Miss Sarah Manning Dawson is also on the panel. She's at Microsoft and has a distinguished history and track record at Microsoft bringing in innovation. So if nothing else, let's watch that panel, but I'm definitely going to tune in when I'm done here. So I'm excited to hear what people have to say about the future of software engineering. After a short break, after lunch, Dr. Ipek Oskaya is going to pick up and frame that in the next session. She leads the Engineering Intelligence Systems group here at the Software Engineering Institute. And the first presentation there is by James Ivers, Mr. James Ivers. He will talk about untangling the knot, which is, I think DoD, as much or more than any other large, and the services as much as more than any other large organization, has a lot of existing systems that are frequently referred to as legacy systems that we can't live without, but are in need of modernization. And so the research James is going to talk about is about how do you understand and visualize large legacy code bases, and then help segment those code bases into parts that can be capabilities that can be extracted and moved to microservices or to a new system, a brownfield or a greenfield system. So it's a fascinating bit of work. After that, Dr. Jerome Hughes, and I think I pronounced that wrong, I apologize. He leads our architecture analysis and description language group. He's going to talk about something called TwinOps, which is really talking about how do we use model-based system engineering and then couple that with high-fidelity physics simulation. So SEI has a long history in model-based system engineering and is one of the founding or early creators of the architectural analysis description language, and then coupling that modeling environment with a physics simulation environment so that we can do analysis of alternatives, verify design and integration challenges. So I recommend if you're into digital twins, I recommend the TwinOps discussion. After that, EPEC is going to have a live question and answer session with those two presenters. And then around 2 o'clock Eastern, there will be a deeper dive by Dr. Sam Proctor on model-based system engineering with AADL and transitioning research to practice. Several big programs, notably Future Vertical Lift in the Army, has been using AADL and model-based system engineering. quite a while. So I think Sam's going to talk about a little about where we've been, and then what's in the future for model-based system engineering. And then again, another live Q&A with Sam, Jerome, and EPEC after that. And then at the end of the day, around 2:40, Tom Longstaff, or Dr. Tom Longstaff, our Chief Technology Officer at SEI, will wrap it all up and bring it all together from the theme of the day. And then I also really would like to point out at the end of the day, I should have been advancing slides this whole time. There we go. There's engineering intelligent systems. Then Tom's going to bring it all together. And then at the very end of the day, we've got 4 concurrent poster sessions. So Sebastian Echeverria will be talking about high assurance software-defined Internet of Things security. The posters, I think these are pre-filmed poster sessions. And then Dr. Mike Conrad and Dr. William Nichols will be talking about investigating the feasibility of integrating causal models for software cost control. And so causal models is more than just is a reasonably new research area that actually tries to tease out not just what are the things that are influencing an output, but what really getting to root cause, which things are causing other things to happen. And software cost control is something that we all struggle with, and I think DoD may struggle more than most. So the poster sessions, I'm reminded, they're live interactive sessions with the principal investigators. So you can access them in the Zoom breakout rooms. So each of these presenters will be live for people that are registered. After that discussion, it'll be Bjorn Anderson. He's going to talk about multi-core confidence. So a lot of our embedded weapon systems historically have used single core processors, and there really are very few modern architecture high performance single core processors available anymore. Almost everything is multi-core. And when you do that, you've got cache coherence challenges and timing challenges. And so Bjorn's been looking at this problem set and made a lot of headway for several years now. So he'll do an overview of that. And also really it's about gaining confidence in your embedded system and your real-time system, safety critical system when you run it on multi-core processors. Then Dr. Dio Deniz will talk about rapid certification of trust in his breakout room. And that is the day. It's an exciting day. I'm excited to watch all of these. I'm familiar with much of the work because I've interacted with the researchers in the past. I encourage you, again, if you have questions, please send them our way. We'd love to link anybody up that wants more information with the principal investigators or the people behind the research. And so I wish everybody happy Thursday. And that's it for me.
Morning, everyone. My name is Anita Carlton, and I'd like to welcome you to day 3 of the CMU SEI Research Review. I've really been looking forward to this session for some time now. Today's showcase session nicely builds on the momentum of a study that the SEI currently has underway called the National Agenda for Software Engineering, focused on looking at the future of software engineering research and development. I'm really excited to chair this research review showcase on software engineering's grand challenges, voices from visionaries. Next chart. So as a brief introduction, I'm the director of the Software Solutions Division. I lead the software engineering research, development, and transition portfolio for the SEI with the specific goal of making software a strategic advantage for the Department of Defense. Next. So as a brief introduction, to just set the context for this session, software is essential to our modern life and controls functions as diverse as the capabilities for our home appliances, aircraft flight control systems, mobile phones, healthcare systems, financial transactions, and digital learning, to name a few of the areas. Individuals, organizations, markets, and governments are increasingly dependent on software. Given the ever-growing dependence on software-reliant systems, an imperative exists to maintain and strengthen our leadership and strategic advantage in software engineering. While certainly applicable to systems operating and evolving today, software engineering leadership is especially critical for future systems that will provide greater capabilities, be more data intensive and interconnected, increasingly utilize AI and autonomy, require larger scale integration, and be increasingly edge driven. To that end, we are incredibly fortunate to have the opportunity to hear from a number of visionaries today, senior thought leaders who will briefly describe how they see software engineering enabling our visions for the future and the major open problems and grand challenges that software engineering should address to enable our visions for the future. Next chart, please. So in this showcase, experts from industry, government, and research labs will discuss software engineering's grand challenges as they relate to their respective fields of work, including nuclear science, university research, defense R&D, supercomputing, AI, tech, and thinking about future battle systems. And now please let me briefly introduce the speakers. First, Dr. Deb Franke, the Associate Laboratory Director for National Security Sciences at Oak Ridge National Laboratory. Dr. Michael McQuaid, he is the Vice President for Research at CMU. Mr. Vint Cerf, Vice President and Chief Internet Evangelist for Google. Vint, I love that title. Mr. Alan Dianic in place of Mr. Tim Dare, and Deputy Director for Prototyping and Software, Office of the Undersecretary of Defense for Research and Engineering. Ms. Sarah Manning Dawson, the General Manager for Microsoft Critical Infrastructure Engineering. Dr. Bill Shirless, Director of the DARPA Information Innovation Office, and Mr. Nand Malchandani, the CTO of the Joint Artificial Intelligence Center. Okay, next chart, please. So here's the game plan that we have. I've prepared a specific question for each of the visionaries. After I read the question, each speaker will have roughly 4.5 minutes to provide their thoughts, and then we'll move to the next speaker and question and so on till we get to Nand, who will be our closing speaker. After that, we'll be excited to take questions from the attendees. So please, as you're listening to all the speakers, be thinking about what you'd like to ask each of the visionaries. Okay, chart 7, please. So with that, let's kick things off with Dr. Deb Frinke. So at Oak Ridge, I'm sure you faced many grand challenges related to your areas of focus of advanced materials in manufacturing, supercomputing, and nuclear science. Hopefully, software engineering has been an enabler to meeting those challenges. How can software engineering enable or accelerate progress in one or any of your grand challenge areas?
Ida, thank you so much for that question. And I'm going to use up some of my precious 4.5 minutes to thank you so much for pulling together this panel. You've got a lot of really great people who are friends and colleagues on the line, and I'm motivated to get done within my time slot so I can hear from them. I love that question for a second reason. I spent most of the last 9 years at the National Security Agency dealing with defense, intelligence, support of the nation's systems, and it's been really an interesting pivot to step back and look at software from the context of what we do in science. And so I've geared my response mainly towards that piece. So what's been interesting for those of you who may not have looked at big science in a while is that you're mainly aware that big science relies very heavily on what one does with the big iron, the high performance computing. Really critical investments in new approaches are equally important. And the algorithms and the data are part of it too. What was a little startling to me is how integral the algorithms and the software itself have become to the scientific process. Because at the time I last worked in the National Lab system, primarily we hired people to write software for relatively well understood algorithms and have them run effectively on the large scale systems. The game has now changed. So for instance, I'm investing in a really cool program that's intended to support a future challenge, future nuclear reactors. They will be smaller, they'll be made and use different processes. And in order for this to be effective and to meet some of the mission needs we have on the non-proliferation side, we need to be able to distinguish amongst 2 different kinds of isotopes of plutonium. So bottom line question, interesting problem. You would think that that had a lot to do with lab work, and it does. But this particular investment I'm making is really more about how do we properly implement the kind of machine learning tools that will take the data that we'll gather and rally that around a solution. And that's an interesting example because what it shows you is that the software is now an integral part of science in that it's not just enough to have instruments that have sensitive detection capabilities and not enough to have horsepower, but you've got to have software. Now, software isn't a lump of code that sits in one place that we can look at anymore either. Software is what comes together in the environment in the moment. So the software in my field, particularly in science, has to do as much with what are the actual elements, what are the actual executables that come together from the many different instruments that are pulling together data from the outside that are being mapped to the high performance computer and that are intended to show the visualization, again, based on software on the system that is going to be used by the scientists in making their assessment. All of those pieces are coming together from many disparate places in many versions. If you don't get the version control right, then you are not going to be able to replicate that experiment. And that's an important aha. Science is now very much dependent on things such as version control and understanding just as much as the data in many cases, because the way that one analyzes the software, the way that one inculcates the data into the machine learning, particularly being the lingua franca of the day, is really necessary for replicating things. And then if you look at that, that creates some additional challenges. Our code writers now are unlike the ones that I worked with primarily, again, about a decade ago, the last time I was in the lab systems, in that they were more focused on how do we get an algorithm to run accurately on big iron, and how we could get the data all in one place fast enough to make the challenge work. Now it's a lot about how do you combine all of those different people and platforms and have the collaboration work correctly. So the software itself is a collaboration tied to the instrumentation. And so it's really a very different thing. You could almost talk about software physical. I know that's not as catchy as cyber physical, but that is really a thing now. And your software physical systems had best be in order. Second thing I want to highlight. From a security perspective, this software is what comes together in the moment to execute. Thinking about some of the other programs in my backyard is really critical. It makes the assurance problem far harder, because it's not simply enough to do the hard work that we've been looking at for a long time in this profession of how do you pull components, disparate components, some untrusted, into one place and gain some assurance. You do not know what you have in the moment. It may have been patched live, and you don't necessarily know who is sharing. So that piece has really changed the game. I'm hearing it's about time. I'm just going to squeeze in, transition to Michael McQuaid. Thank you.
Thank you. Thank you for those great insights, Deb. I'm going to remember cyber software physical systems. That's a good one. Next, we'll have the opportunity to hear from Dr. Michael McQuaid. So as the Vice President for Research at CMU and co-chair of the Defense Innovation Board Science and Technology Subcommittee, can you please describe the challenges you see in bringing research to practice and discuss ways that we could bridge this gap, including strategic partnerships with industry, government, academia, and research labs? And Michael, I ask this question because as we think about the future of software engineering, we'll need to think about how to enable strategic partnerships and collaborations to drive innovation in our broader ecosystem.
Great, thanks Anita. And since I'm the one on the agenda with a CMU tag under my name, let me also thank the other panelists for joining us, and for all of you, welcome to CMU, if only virtually. So great set of questions. Let me ground it by taking a step up for just a second. First of all, I will tell you that I never lose an opportunity to espouse the virtue and unique competitive position this country created over the last 100 years of this amazing triumvirate of frontline universities doing basic research, often sponsored and paid for by the government laboratories who do a combination of fundamental research and directed research, and a country that has an extraordinary component of private sector companies that are not just doing research to get the next product out the door, but are doing research for the long term. That triumvirate has created the world we live in today. As an aside, we should not be surprised when our competitors try and replicate that model, and that's a competitive world we live in. But take that for just a moment, because I want to make the point that software, and maybe by analogy, AI and other things, can often change that model. In a world where particle physics which is where I grew up, particle physics was always done at a national lab or a university, and private sector companies would then use the benefit of that research to turn it into commercial products. Things like software, things like AI, the research is as much done in the private sector as it is done in academia or the government. That means we need to think differently about how we bridge the gap between research and commercialization. The second thing I would say is that software and related fields oftentimes these days have a much shorter clock cycle associated with how rapidly things go from research to implementation. And in many cases, we have the opportunity to try by doing, which is a different model than what you might do at a particle accelerator. So keeping all those things in mind, our world is changing and we need to be aware of that. Our traditional models for how we transition technology to the market are different than they were. What do we need to think about from an action? First of all, it is vitally important that those people working in our research fields understand the potential applications of what they do. So when we think about programs of exchange and transitions and rotations, we are very, very immature in that. Our ability to move people in and out of government, our ability to move in and out of academia and in and out of industry needs to change. So point number one. Point number two, we have to educate leadership in each of those three environments much more vigorously on what technology might do. You know, we never want to be in a situation where somebody says, oh, just go get me some of that AI and I will solve all my problems, whether that's a battlefield problem or a product problem. So educating decision makers on the what technology might do is critical. And third, I would just put a very strong marker down for programs like the NSF I-Corps program, which are fundamentally about teaching people who want to transition research what that really means. What does it mean to talk to users? What does it mean to have users talk to you? What does it mean to have people embed with you? What does it mean to really understand how I can evaluate a potential market or a potential product in that market? Additional thing I would say is we need to get the balance on the research side right. There are two answers at the extremes, which are extraordinarily situationally dependent. Neither answer is generally right. So one answer is I have a challenge, let me fund research to meet that challenge. The other extreme is I have some technology, let me work on it, and then we can figure out what it's good for. They both have a place. They are not general solutions to the problem. So constantly thinking about where we need to be on that continuum, I think, is extraordinarily important. And then finally, I would just reiterate what I said before, making sure that our researchers have a much stronger connection to what the application might be. I'll bow to Bill's catechism of you know, if I'm 100% successful, so what? But we need to be thinking about that from our research from the very beginning. What can it do if it can do what it said it was going to do? And with that, I think Vint is up next.
That's awesome. Thank you, Michael, for those great considerations. Yeah, as we start putting all these various ideas together about the ecosystem and the different roles and responsibilities, you really gave us some great considerations. Thank you. So next we'll have the opportunity to hear from Dr. Vint Cerf. So Vint, you're known as the father of the internet for the design of the TCP IP protocols and the architecture of the internet. TCP IP offer just enough constraint for standardization and just enough freedom to foster proliferation. What's the equivalent from your perspective of TCP IP for engineering large-scale software-enabled socio-technical ecosystems?
And tell me all about the universe in 25 words or less. Okay, it's a great question. First of all, let's warn the audience to distinguish between vision and hallucination, and these need to be carefully, assessed. And second, I'm not going to lose an opportunity to urge SEI to work really, really hard on bug prevention and discovery, software to help avoid making stupid mistakes that later can be exploited by the bad guys. We are not good at this yet, and I look to SEI to really work hard on that. But to answer your question specifically, I would start with the notion of minimum viable product. What's the least that you can get away with to satisfy the most important of your requirements? Second, anticipate iteration, both to satisfy additional requirements you've already identified, but also to discover later, as things are in use, new functionality that might be needed. This is sort of like people say, you know, how do you sculpt things? And the sculptor says, I chip away everything that isn't the sculpture, and then I end up with what I want. One thing which is very important in design is getting to the right level of abstraction. If you're too low a level, things get very confused very, very quickly. If it's too high a level, the model isn't very helpful. So adjusting the level of abstraction for design purposes is very, very important. And then you want to analyze the design for its opportunities for expansion. In the case of the internet, it's a layered architecture. The layers of protocols have very well defined and have had very stable interfaces between the layers. You can add more protocols in any particular horizontal layer, and that has happened. For example, HTTP came along and introduced the World Wide Web, thanks to Tim Berners-Lee and his colleagues. And that was a layer of protocol on top of TCP/IP, for example. So many protocols have been added at new layers, and many of them have been added in horizontally. You want to make sure your design has this kind of expandability. I want to also reinforce what Deb was saying about version control. That's super important when you're dealing with software. And her notion of just-in-time software, which sort of meets at a certain point in time, is vital in a network environment where every time two machines interact with each other, it may be an experiment that's never been done before. And we need to be aware of the fact that things are not necessarily all locked down in these kinds of environments. So in the last point, I think, is that the application programming interfaces and the libraries that serve them are vital parts of today's software world. And it's important to maintain those libraries and to make sure that they are safe and secure and are bug-free. And I can tell you that running off to source code does not necessarily guarantee you bug-freeness. In fact, if anything, since everybody's in charge, nobody's in charge. And so we should be very cautious about using open source libraries and to double check to make sure that they are, in fact, as secure and safe as we want them and need them to be. So I'll stop there and look forward to some discussion with the attendees at the end of this session.
That's great. Thank you, Vint. We very much appreciated your points and your perspectives. Next, we'll have the opportunity to hear from Mr. Alan Dianic, who's here for Mr. Tim Dare. So in your roles with OSD R&E, you have responsibility for a range of software and system engineering activities. And so as you think about the future of how software will be developed, what is the grand challenge in rapidly developing and deploying software reliant systems based on user intent versus only on user requirements?
Thanks, Nita, and thanks for the opportunity to speak, and certainly thanks to SEI for putting this together. Within DoD, a focus is obviously operational systems that have some critical functions. And so we're very concerned about getting behaviors and trusting them with behaviors that can in some cases be fairly significant. One of the things that we would want to make sure we understood is certainly how you capture intent. What do you mean when you say, I want to have intent? We need a sort of a stable set of semantics that allows us to communicate. We understand that in our operational environment, there are many unit entities that have very different ways of communicating similar information. And so what we want to do is first of all, make sure that we can define the method by which we would translate that intent. Certainly we understand, as imperfect as it is the current development environment, we understand some of its limitations and in terms of being able to go faster and sort of not being stuck in some ways with a waterfall heritage where we're trying to move much more quickly and deploy software that is resilient and more responsive to operational needs. So, but understanding the semantics by which we would be able to capture that intent moving forward. But a major impediment, I think, in any of these systems, and not to steal anyone else's thunder, but to jump on, is really the data problem. In any system that we're trying to leverage, particularly things like AI machine learning, we have a tremendous data gap in our environment. Acquisition of systems very often leads to data stovepipes and data that's basically parked behind very difficult firewalls. And that's a quantity of data that would be necessary. Really a need for a sort of the unification, but not only of data, metadata, but really kind of a meta semantics. What does the data mean? And the same format, same type of data may look and appear very different to different parts of DoD in their operational environment. And in some cases, some data requires a cultural context. How do I interpret this? Say a call for a certain type of action. In some environments, that requires a concurrence or an authorization. In other environments, it simply is the request will be fulfilled unless there's a denial. How do we capture that kind of information so that the systems will do what they're intended to do with a consistent set of expectations? And of course, when you start to look across information security, we have a unique problem in DoD in that we not only have at the top level security management and usage management and what's appropriate to do and how it's appropriate to use our data, but also data aggregation. When data comes together and we may very quickly get to a place where we have to really understand how that data is going to be controlled so that we don't have spillage of information that's very sensitive. So all of those things are going to be critical. And then operations, when we talk about intensive systems, and operating in a contested environment, we assume that future environments are going to be denied. In many of the things that we've come to rely on in our information systems and our command and control systems are going to be denied. So how do those systems continue to operate with various kinds of degradations that may be very difficult to predict? How do we make sure that the intent of the system to operate continues to operate even when there's a lack of communication or there's a sudden lack of positioning data or other kinds of things? So those are some of the areas that we think would strongly impact that and would be a concern going forward.
Great. Thank you, Mr. Dianic. We really appreciate your points. Those are great considerations. Next, we'll hear from Ms. Sarah Manning-Dawson. So we can't discuss grand challenges or grand opportunities without focusing on the primacy of data. Alan Dianic just brought up some of the data issues. So in your work in engineering the hyperscale cloud, what advances are you working on that will enable the kinds of data use, protection, and integrity that are a necessity for any advancement of software engineering?
Yeah, thank you, Anita, for the opportunity to be here and to share a little from my experience at Microsoft. I think the term data primacy here is interesting because people often think of data in terms of the stateful data, right? The stuff that lives for a while sitting on disk. And really, data is at the center of everything we do in cloud computing. You know, it's what the compute environment is acting on and reasoning over through processor and memory. It's what we send over the wire or over the air, and it's what we store on disk. So, you know, when I think about the journey of where we've been and where we're going in the hyperscale cloud, particularly in the context of use, protection, and integrity of the data, I think we faced some unique challenges around how to operate the cloud while engineering our services to ensure the confidentiality and integrity of that data and, you know, the users of it. So I would say probably the biggest two innovations or advances in service of these challenges is number one, confidential computing, and number two, what I'll describe as the increasingly distributed computing environment that we call cloud, but that really exists across endpoints and users, edge, and the hyperscale cloud. So to delve a little further into confidential computing, you know, imagine you're an organization or a company, you've had a compute environment on your premises for a long time, whether it's in your basement with your IT staff or you've got a local data center, and you make a decision to move to the cloud. You know, especially in the earlier days of cloud services, there was understandably a lot of angst around losing control of that environment. Because by definition, right, moving to the cloud means moving your environment, the operations and the management to someone else, somewhere else. And, you know, it was very important for both cloud service providers like us or Amazon or Google to, you know, be able to let cloud users know that no one would touch their stuff, right? And for these cloud users to know that too. And so, of course, we started with sort of well understood security goodness, like offering strong encryption on disk and over the wire. But our users want to know that even when the data is in use, so the data in memory is kept private. They want to know that if operators have admin access to the machine or the operators are physically present in the computing environment, the data is still held confidentially. And so confidential computing, which is tethered to a hardware-based root of trust and not the software of the cloud provider, completes that promise across the full computing environment, including data in memory. So not just data at rest, not just data in transit, but data in use. And we're seeing this technology being offered in all of the major hyperscale cloud providers, which I believe is good for our cloud users and good for the promises around data confidentiality. The second thing I mentioned is this increasingly distributed computing environment. And this one we're really in the early stages of, but it is pretty exciting because it sort of changes the definition of the hyperscale cloud, right? It's an incredibly powerful and scalable processing environment. But as cloud computing broadens its reach and moves deeper into digital environments beyond traditional IT, like to power substations or oil platforms, we're encountering unique needs to have options to process some things on location, whether it's because of network isolation, intermittent or costly connectivity, data sovereignty needs, or extreme low latency needs. And so what we're seeing is that in response, cloud providers are creating smaller and smaller scale data center form factors. So think of these as micro data centers that we can deliver to a power substation or a military base or an oil platform. And it really blurs the lines between the hyperscale cloud and the edge. So we're also seeing this being offered by major hyperscale cloud providers as well, and really excited about this road ahead. Thank you.
That's awesome. Excellent insights, Sarah. And I see that within our panelists, there's some comments and on confidential computing. So we'll come back to that at the end of our session. But thank you. So next we'll have an opportunity to hear from Dr. Bill Shirless. So Bill, the question that I've thought about for you is, at DARPA, you lead program managers in the development of research, technologies, and advanced capabilities to ensure information advantage for the United States. How extensively does information advantage overlap with software engineering advantage? And what are the primary software-related areas you feel will lead us to advantages in both realms?
Thank you, Anita. That's a very broad question. I'll just try to touch on some of the key points. I'm going to start with 3 general points about why we do what we do. And the first is that the information domains that you mentioned almost entirely manifest their capability through software. As we all know, software is everywhere. There's more of it than before. It's in more significant roles. It's the favored building material in the military sense, both the non-kinetic and the kinetic domains. A second general point is that, and this is very important, our software practice stays creative. And what I mean by this is the engineering of software, that practice will not be routinized, although we must struggle continuously to make it so. And this is a kind of a conundrum, and this conundrum exists because with software, we're unshackled by the laws of physics, and so the abstraction level continues to go up without bound. And this means that we're able to connect more closely with our domains. That's the pull. But it also means we're never going to fully automate software construction. A third general point I want to make is that software is the enabler for nimble engineering. This came up earlier, Vince remarks, and several others as well. This idea, which at DARPA we call it the pipeline, is a broadly expressed aspiration now in the DoD. It's been the standard of practice in the SaaS world, in the commercial sector for decades. But in our world, there are formidable challenges to manifesting it. And the idea is to blur prototyping, development, and sustainment, where sustainment for software is really evolution. It can start with an MVP, minimal viable product, as Vint pointed out, but it does not always start with traditional requirements, but rather a sense of the scope and mission and the intent, the general area of intent. It's also designed from the outset for integration and interoperation. Whenever you hear somebody from the government talk about an interoperability problem, you know that it's not a technical challenge. It is always a challenge of business models and incentives and the will to engage. The pipeline models have become an imperative for three reasons. One is that the threat environment that we face now is nimble and capable. Both peers and non-peers can pivot rapidly. We have to be able to do the same. We can't go with the model, we used to call it the requirements delay surprise model, where years go by and then you get something that turns out not to fit the need. The second driver is the technology advance. Obviously, everybody's talking about AI, but there are a whole range of other technologies that also are being brought to bear. And then the third is the consequent fluidity of mission concepts with hybrid domains, modern battle management, and the like. So I've got a minute left. I'll mention some areas of research. I've got actually 4 broad areas, and within each about 3 or 4 particular technical areas. So I'll just mention the 4 broad areas. In each of these areas, the 13 particular challenges and all that I was going to mention, there are DARPA programs in all those areas. So if you want to connect with those, please reach out. The first is what I'll call software-enabled complex capabilities. For example, how do we engineer systems that embody AI and machine learning capabilities? Generally, when we're talking about AI, we're talking about not just machine learning, but hybridizations with game theory, knowledge representation, search and planning. And so we have to think about how to build trustworthy systems from these inherently right now flaky components. But it also includes, for example, IoT and CPS. The second broad area are what I'll call software structures, architecture, human system symbiosis, performance technologies, data engineering, security engineering. Third broad area, software engineering models, analyses, and evidence, formal methods at scale. For example, engineering traceability and evidence, program understanding. And then the fourth area is software engineering activities and infrastructure, test and evaluation, continuous ATO, authority to operate, tools, data. Software engineering is a very data intensive business now. And all that data manifests evidence that we can then apply. And then also, of course, model-based approaches. So my fundamental final point is we have to stay focused on advancing our software capability. We also have to figure out how to adapt our business models to make these things work. Thanks very much.
Thank you. Always eloquent, Bill. Thank you very, very much for all of your insights. And now our final speaker, before we get to some questions and comments, Mr. Nan Mulchandani. So the DoD considers AI to be one of the keys to national security. What are the key AI engineering challenges that must be solved so that AI can live up to this promise?
Thanks, Anita. And let me see if I can sum up all of AI in the military in 4 minutes here. So one of the fun parts of working at the DoD around AI is that everybody immediately jumps to their favorite disaster movie involving robots. So it's either Terminator and Skynet. And I think the way to think about this is that people are thinking of artificial general intelligence as being applied to all these problems. So the big question is, I personally don't know what it's going to take to get AGI out of the realm of science fiction into reality, but there's a lot that can be achieved along that axis. And so let me see if I can articulate some of this in a structured way. So when we think of applying AI and the software engineering challenge of bringing AI into the military, I typically have been starting to call this software-defined warfare, in some sense, sort of pulling from what we've done in data centers in industry and others. And some other people call it things like military Internet of Things. But regardless of what you call it, there's sort of 2 big things that we think about in this area. And the first is what we think of as autonomy, which is, think of at the tactical edge, a set of autonomous, reconfigurable, hardware systems that's really focused on human machine teaming, sort of in a local way. So think of special operations, think of the unit level of things happening on the ground. And the second A is automation or orchestration, which is really, a lot of people think of this as swarming, or other types of algorithms, but basically pulling all of the backend information together, both from a logistics, intelligence, readiness, blue and red force tracking, et cetera, all of this pulled together and moving it from the intel side to the ops side. And this is really the focus of what we're thinking of when we talk about missions like JADC2, which is Joint All-Domain Command and Control, or ABMS, which are the Advanced Battle Management System projects going on at the DoD. So you've got the local piece, which is autonomy, and then you've got the automation piece, which is really about connecting all of these things together. So that's really generally how I think about the problem, sort of in a very simplistic way. So let me now move to the sort of software engineering challenge side of this. And I break this up into what I think of as the supply side and the demand side. And on the supply side, you really have obviously industry, academia, CMU, obviously great research institutions doing huge amount of work on advancing the state of AI. And in there, you've really got what I think of as an x-axis and a y-axis. So on the x-axis, really you're thinking of narrow AI, which is a set of building blocks or domains that we can apply different algorithms and different techniques to, such as image recognition or NLP or full motion video object detection. So these are on the x-axis. And then on the y-axis, you've got the AGI axis, which is really about starting with things like predictions and reasoning, and then moving your way up maybe to infinity, where you get to things like AGI and truly sort of human thinking, which is generally what most people think of as there. Now, the good news is on the narrow AI side, the x-axis, we are making a lot of progress. There's certain domains and areas where we read about in the news, some computer system beat some champion in some area, or the AI system is able to play Pong really well. So, however, in the military, as you can imagine, we're dealing in the world of physical hardware, we're dealing a lot with vision, we're dealing a lot with the tactical edge in a denied and degraded environment. So, even at the outer edge of the x-axis, we're dealing with technologies that are not really scaled. So things like Project Maven, for instance, you may have heard of, around full motion video object detection, still very, very hard. The really bad news is that on the y-axis, around reasoning and things like pattern of life and other things, we're still very, very early on. And so the idea around being able to assemble and reason around these objects is still very limited. And the last thing that I'll end with is, so there's a supply side of that where we're, I think, still in the sort of lower, sort of lower part of the quadrant, if you may, when it comes to the supply side. And then on the demand side, the DoD just needs to do a better job of being able to integrate and receive this technology. So first thing is architecture. One of the points is AI is living software. There's an entire loop of being able to develop and deploy AI software continuously, trust in the system around explainability, data issues, and these are all problems that we still need to do. So if I were to sum this up, the supply side is getting better, but the demand side itself requires a huge amount of work, which is probably where the biggest software engineering challenge lies. Thank you very much.
Great, great. Thank you, Nan, for those incredibly insightful comments. You gave us a lot to think about in terms of the supply and the demand side. So we have, what I'd like to do is, before we take questions from the audience, I would like to ask the panelists if they would like to comment on what they heard their fellow colleagues talk about, or even ask a question or two to their colleagues. And we've had this chat window going. So I know, Vint, you'd like to maybe kick off just a few comments. And you wanted to reinforce the idea of confidential computing, something that Sarah talked about.
Yes, thank you so much for giving me that opportunity. Sarah, you and I are both, I think, equally excited about confidential computing. It just adds a whole other dimension to protecting customers' information and their software in a way that isolates them not only from everyone who is sharing the cloud, but also with the organization that's offering the cloud. And in our case, of course, it's at Google. In your case, it's at Azure. So I just want to reinforce that that's a game changer, I think, for a lot of people who would otherwise be reluctant to commit resources and their company's assets to cloud-based computing. The second thing I wanted to bring up has to do with open source. There was a comment about it in the chat. And I would say that if we think of open source as a gift horse, then make sure you look it in the mouth carefully. As opposed to not doing so. I would see open source as a wonderful opportunity to get access to software, but at no time should you make assumptions about its safety or security, particularly given what was said about the idea of just-in-time coalitions of software interacting with each other that Deb brought up.
Awesome. Thank you, Vint. Deb, I know you wanted to comment on this idea of nimble engineering that Bill had talked about. So Deb, I'll open the floor up to you for a minute or two. Oh, Deb, you're on, yeah.
There you go. So thank you. And I'm hoping Bill will dive in as well. So also want to foot stomp. Confidential computing is going to be absolutely critical for science, especially as social scientists, because we need to have a way to effectively work with that data without revealing individual components. So that's a must-have in my view, and we really need to be investing more on that from the scientific side as well as the military side. Open source, agree entirely as well. Gift horse, it's always running with us. But the nibble engineering I wanted to hit, partly because I think this is another must-have, but I'd like Bill to talk a bit more about the safety issues involved. We must have it because we need to have a way for collaborations to come together quickly around a problem. COVID was a great example. There was a great deal of excellent work done in order to pull different software models, essentially looking at the analytics, looking at potential for vaccine. It happened without the time for the normal checks and balances. How far can we go and how far should we trust the nibble engineering, I'm wondering, and Bill, I know you've thought a lot about that, so perhaps you could take a little time and go further.
Thanks, Deb. This is a really significant topic for us at DARPA. We're looking at nimble or pipeline models in two respects. One is as a means to support the transition of technologies from the lab into practice, into the supply chain. This was a point that got raised very early by Michael. We implement that model, for example, with respect to cyber capabilities, and as Nand knows, we're working with the JAIC with respect to emerging AI capabilities. These are fast-moving areas. We have fast-moving threat environment. Fast-moving thinking on what the mission capabilities ought to be. We have to have the nimbleness. So that's one aspect of our engagement. But the other aspect of our engagement is in developing engineering, tooling, technological foundations, scientific foundations, mathematical foundations to enable nimble practices that address the challenge that Deb pointed out, which is how do we get to high levels of assurance for these fast-moving systems. Most people in the software world are familiar with the Ariane 5 story from the European Space Agency many years back. That's a story about an engineering team that did not want to go through the gate of authority to operate, and so they kept the old software that they knew was broken. And so the costs and uncertainties of these evaluation gates are a significant impediment. So our focus here is on the accumulation and management of this large body of evidence. I pointed out earlier that software engineering is a data-intensive activity. We have models, we have analyses, we have test cases, we have the code base, we have the full history of the code base. If we can build formal structures around this evidence, argumentation structures, safety cases, hazard analyses, all the various things, the models that engineers are familiar with, then we can actually use our tooling to have all this evidence fly in formation in a way that that we can predict the outcomes of these evaluation gates. This is a very much an emergent phenomenon in the safety critical community. But if you look at the very best commercial practices, since Google and Microsoft are with us, there are two great examples of this. We see a lot of these ideas showing up in these practices. So the idea of evidence flying information is one key thing. Secondary is the architectures, the way we organize the components of our systems into aggregate capabilities. We have to think about architectures in a way that we get for incremental effort, we get incremental improvements in capability, and then incremental activity to recertify those systems. So that notion of incrementality is key. That's enabled by architectures. Think about the framework and apps on your mobile device, but also the way web apps are constructed, for example, the NPM ecosystem, or even the old-fashioned big data with Hadoop and its family. In the military context, former Chief of Naval Operations, Admiral Greenert, talked about platform and payload with respect to the engineering of systems. These ideas are fundamentally significant, the architecture. And then the third piece of it, the 3 A's, assurance, architecture. The third A is activity, or you think of it as agility. It's the practice, the process of following the Agile ideas. The only way you get to Agile at scale is with architecture. Otherwise, you can't scale up beyond the 6 people in the room. So you put those 3 pieces together, you get something that works. Now, the Defense Science Board, Paul Nielsen, the director of the SEI, was a co-leader of that activity a year and a half ago. The Defense Innovation Board, Mike McQuaid, was part of that process. Both of these groups have made recommendations that tilt very strongly in this direction. So I think this is really an important capability for us to develop.
Great. Thank you so much, Bill. Sarah, I know you had a question for Nan. That'll be maybe our last question amongst our panelists, and then I'd like to take a few questions from our audience. But Sarah, I know you had a question for Nan.
Yes, thanks, Anita. And pardon the light. I'm in Seattle, and it's the first time in 2 months that light has come in this room. So I can't complain, but I know it might be strange.
Solar therapy.
Yeah, I'll take it. Nand, you had described the x-axis and the y-axis, x being some of the current AI tech, and then the y sounded like a description of how it sort of ups its game to becoming more and more sophisticated. And I was just interested in your thoughts on which aspects of those x-axis items you feel are climbing the fastest, and what does the near-term future look like?
Well, thank you. Well, I mean, I think the news reports glow a lot on the sort of left hand of the x-axis, right? You've got things like NLP and image recognition, et cetera. Any kind of bounded problems where sort of you can apply huge amounts of compute, or the algorithms are skilled, et cetera, I think are doing incredibly well. The place where we're starting to struggle is, as I said earlier, where we're moving to the right on the x-axis in terms of UAV, full motion video object detection, right? Huge problem just in the basics of being able to identify objects, different lighting structures, different sensor technologies, and that too in the mode of adversarial AI, right? Where if the data gets leaked, if the algorithms are well known, et cetera, there's easy way to spoof these highly bounded algorithms that can perform very well with good training data sets that are bounded and algorithms that are, I call this looking for the keys under the light, which is once you've bounded the problem, you can do a great job of extensively doing something there. But anytime you go outside of it, the explainability, the ability to predict and control that, especially from a commander's perspective, when they're throwing, people and you're doing targeting and a number of other things that are very, very tricky to do. And also you want to do them incredibly well and with discretion, becomes incredibly hard. And then on the y-axis, once you have the building blocks there, you can identify what we call dots on a map, say, the ability to reason about them. So just take the idea of tracking 2 cars on a road. Are they moving together? Are they together? Are they trying to overtake each other? Is one trying to crash into the other? Are they driving on the right side of the road? We can't even make basic, just even from the current tech, the ability to reason off of dots on a map itself is incredibly, incredibly hard. A aircraft getting refueled at a base, for instance, what does that mean? Where are they going? What are they going to be doing? Where are they deploying to? So anyways, huge unanswered questions. So however, the last thing I'll say there is, even though we're there is this aspect of we're really behind, what typically happens is things are slow, and slow. There's some breakthroughs and inflection points, and all of a sudden, something that we had envisioned that would take 20 years, all of a sudden appears out of nowhere. So anyways, thank you for the question. It's great. Thank you.
That was a great question, Sarah, and I really appreciated your response on that. Michael, I wondered if you could comment on the Defense Innovation Board study, Software is Never Done, because there were several questions in the chat about what that really means. And so I thought maybe you could really comment on that.
Great. So thank. Let me make just 2 comments on what it is and 1 comment on what it is not. And as always in this circumstance, it's always good to have smarter people already make the point. So we specifically chose Software is Never Done as the title of that report to accentuate 2 things. 1, Vin talked about this before. You simply don't do software by requiring it, writing it, testing it, and then rolling it out to the field. That is simply not the way any sane and rational person or organization does software. And that was important for us because it led to a series of recommendations about how you fund software. So if you don't do software that way, funding software by saying, write all your requirements, then we'll write a contract for you to develop software. To prove to us it's all right, then we'll write a contract to deploy software. So Software is Never Done means software is an evolving capability that you roll out and improve. Bill made the second point, which is Software is Never Done is also a statement that software is not a physically constrained object. And while the physical instantiation of the compute may constrain you, or the comms may constrain you, or the sensors may constrain you, the software does not constrain you. And looking at how software can evolve to meet mission needs is another reason we use that term. What it does not mean, and we don't stress this enough, it doesn't mean you do crappy code. It doesn't mean you write software and it's okay if it's not any good because we can fix it later. That is precisely not the intention of Software is Never Done. I stress that because anybody on this call, anybody listening in who ever has to go argue a program to a funding agency, anybody who has to argue a program in front of a House staffer or a senator, please don't say Software is Never Done because we never get it right.
Great. Thank you. Thank you. Okay, I'm going to take we only have 10 minutes left and there are so many questions. So let me see if I can get to a couple of them. And Alan, there's a specific question I'd like you to address. I have that teed up too, but first from Patty, it's directed to you, Nand. Do the DoD trade-off technology decisions limit us from achieving the transition to AI? That is, not all domains or infrastructures are equal in data, infrastructure, or operational use.
Yeah, that's a tough question. Let me see if I can answer this quickly. The way to think about it is when you're evaluating investments, there's sort of 2 ways of thinking about this. I think of this as the vitamin versus the painkiller problem. And what tends to happen is the headache or the toothache typically gets the money first, right? It's one of those things where you can recast a project one way or the other. And in many cases, a great example is logistics, right? Not the hottest, most exciting thing. You're not going to get a science fiction movie about logistics. That's a blockbuster, billion-dollar blockbuster. But as they say, amateurs study tactics, experts study logistics, right, in the military. And so it's one of these things where the hottest thing gets the investment and the tech, while the sort of more important stuff typically languishes. So I think the audience member who asked that is right on, that typically sometimes we won't make the right trade-offs. But applying good business practices and thinking about how to do investments with return on investment, et cetera, is something that I think we need to obviously do a better job in the government. But it's just like any other large enterprise where, you know, there are all kinds of trade-offs, whether it be tech trade-offs or business trade-offs or politics. These all things come in. So the answer is yes, they do limit us, but we're obviously always striving to try to do a better job of that. Thank you.
Thank you. Thank you, Nand. Alan, I thought you could at least start by fielding this one. It's a workforce question. What actions need to be taken to ensure that the U.S. has the workforce talent to take advantage of the opportunities for this software-enabled future? So I think that's something that you and Mr. Dare and other folks in OSD R&E are thinking very critically about.
Oh, so give me an easy question. So I think that is, there are a lot of challenges there. I think structurally, and here's why I try not to get fired, structurally within the government, it can be difficult to find and retain folks. In my experience doing software commercially and as a contractor, very often we change jobs because we wanted to go on to the next cool technology, right? We wanted to move on. It really wasn't so much about money. Money helped. So how do we keep those, how do we create that environment within our own space, within the government, so we have people who are challenged, they're moving from effort to effort. I think there's a part of the job that's really based in mission. So when you're participating in mission, that's an additional call beyond the technical part of it. But I think a lot of it really has to be, maybe some partnerships, internships. We've been working with a couple of organizations, one funded study to look at this, and also the software workforce group internally. And there's been a lot of discussion about doing this. And there's not going to be one bullet, because software commercially is moving very quickly. In the government, I think we tend to try to, well, let me have an aux series, and let me categorize this in this way, and then you're going to have this progression, and the system tends to favor seniority over skill. And so what we need to do is really think about, the appropriate distribution. What kinds of things should we contract for, right? The kinds of skills, the kind of activities it's better and more efficient. And what kinds of things do we really need to own inside? And how do we make technology available so that our very smart warfighters can actually take that technology and apply it in a mission relevant way? So hopefully that wasn't too long or off topic.
No, that's
over.
No, thank you, Alan. Thank you for those insights. I know that's a pretty broad question, but I just wanted to, I know this is something all of you OSD R&E is thinking about critically. So thanks for those comments. There's a question from Donna for Dr. Franke. As we move forward with quantum computing, how do you see AI aiding and helping to rewrite algorithms from the existing HPC software and weapons codes for modeling and sim?
Great question. And that's one that's a lot of people are very enthusiastic about. I have to put in my little bit of a plug. Really, the quantum sensors are a thing we can think about nearer term. We've got the ability to build those now and so on. And when we talk about quantum helping in this context, we are likely talking about high performance quantum, at least possibly medium, high, intermediate, but more likely high performance that's bracketed between two classical systems. So you're probably looking at something like that. But in that context, there are many people trying to seek out whether the architectures tied to a qubit-based motion and the ways that you can compute with very large numbers of quantum might be more appropriate for some of the advanced simulation and modeling needed in that area. One that I'm especially interested in is fallout, because that is really complex when you've got to get weather conditions, direction. There are just a lot of interesting things that need to be looked at. A hesitation that one must have when you're looking at the weapons codes, especially it's tied to very sensitive data and models that are used and calibrated versus using classical methodologies. And so you can't simply move to a new model. You might have different outcomes. There needs to be some way to correlate the results you get from a classical approach. Again, the software being part of the sensor, you've changed sensors in essence. When you change models, we'll go to quantum. So that would be a caveat, but a lot of people looking at using something like this when it becomes available.
Great. All right. And possibly this is the last question. It depends how quickly we can get through it. And it's from Tom Longstaff, our CTO. So to avoid fighting the last war, how do we define and embrace a new way of looking at vulnerabilities, bugs, and defects in increasingly complex and emergent systems? I don't
Are
know.
you looking for somebody to respond to that?
Sure. Would you like to kick it off?
Well, just a short one, and that is to pay much more attention to trying to model what it is that software is trying to do. Modeling and testing of models is probably better than trying to build a theorem that says the program does what it's supposed to do, because we've broken our pick on that. But models are very valuable in my view, and also looking for invariants that could be tested for an operational piece of software as another tactic. None of these solve the entire problem, but paying a lot more attention to it would be helpful.
I'll build on that. That's incredibly important for working in the large. There's also an in the small that needs to be considered. So in the moment execution is the bringing together of all those disparate pieces. Adversaries can, for the next war, certainly become adept at pulling together small components of executables. They already are, in terms of stringing together and making their own code running live based on what's already on the system. So the ecosystem is part of the issue. So if you can combine Vince's description of what we need to do in the large with an additional focus in the small, you've got a good breadth. I would caution us from thinking we can forget the last war. Unfortunately, the last war is always available to the adversary due to legacy systems.
I pile on one last comment, which is that there are many models that we must use. They are proliferating. That's good. Each model lets us focus on one aspect of the system that we care about independently of the other aspects. The more the better. And the reason the more the better is that what we do not model is what we do not understand. And from a security perspective, a side channel is a channel that relates to some aspect of the system behavior that is not modeled.
Great.
And one more pylon, just to give you some, just one more thing to think about as you think about what crazy things will happen 25 years from now. One of the things we talked about confidential computing, and sometimes we talk about secure computing. I actually worry, to Deb's point, when I have small executable capability, I actually worry about the day when an adversary goes into battle without compute, but just absconds compute from what's available in the battlefield.
Yes, great. I am going to ask one more question. Alan, I'm hoping maybe you could take a shot at it, but really anyone, and this will be our last question, and it's on systems engineering. And I think that's another really important perspective for all of us to keep in mind. It's from Ranjiv. What are your thoughts on how systems engineering could provide a holistic perspective on the relationships between AI, fusion, human adversaries, context, et cetera, on software engineering?
Okay, another easy question.
I know.
So I'll start off with saying when I was a software engineer, and I learned from some very good people about software engineering, and when I switched to system engineering, I realized this is just good software engineering practice. It's something that simply has to expand, right? System engineering was making, from my perspective, various kinds of software work across multiple platforms that included different types of hardware and different types of software embedded capabilities. And I think as you're expanding, the one thing you can't do with it is make system engineering the thing that slows everything down. Because one of the knocks that I've heard on system engineering is, oh, I can't afford 6 months to do requirements. Well, that's not a good evolution of systems engineering. What really has to happen is that process has to continue to evolve to provide its conceptual benefit without adding time, right? And whatever time you take for it, it has to contribute to the ultimate quality integration of the approach. So I think it's an important thing not to forget system engineering in the rush to move forward, but we can't let it stretch out. Over.
Thank you. Well, I guess we really are out of time, but please let me end the session by thanking all of you wonderful visionaries, your enthusiastic participation, the way that you think about and frame some of software engineering's key open problems, considerations, visions, and the grand challenges. And of course, I want to thank all the attendees for all of your engaging, wonderful questions. So thank you all. And I think that we're going to take a very short break before we return back to the research review. So thank you all.
Well done, Anita.
Welcome to the CMU SEI Research Review 2020.
Probably DevOps should be renamed to Arc DevOps. So you just allow some time for the architecture, and really you design, you implement, and then you support. And this is the life cycle. So basically you have to allow some time for the architecture, for big view and design a bit of upfront. And you can distribute that throughout the different sprints, and or have a different swim lane, and then just have it as an ongoing process. It's a practice. So it's just not a state.
When you look to all of these areas and sort of the places within DoD that are really leaning forward, like F-35, do you see them as very similar to what you know about in industry? Do you see much difference between what they're doing and what you've seen sort of in the industry side? How big are the differences between DoD and industry?
Wow. I do think we try hard. DoD has a history of considering, government in general has a history of considering that it's the phrase we use is a special snowflake. And we've been trying hard to dispel that notion that we're not all that different, that the software challenges we have and the software programs that we have can use, by and large, a lot of commercial best practices. I think some of the differences, though, are a lot of our programs are embedded programs. So some of the continuous integration, continuous delivery, and agile approaches, I'm a proponent that they can and do work well on embedded programs, on safety critical and embedded programs. That's something the industry is still working to discover as well, and there's open debate there. So, and then a lot of our programs have humongous legacy code bases. Yeah. Programs like Aegis is one of the ones that I visited early on and have done some interaction with. They've got a common source repository that is upwards of 20-ish million lines of code, and the Aegis weapon system writ large is a massive amount of complexity and subsystems. And I think they have well over 1,000 developers that contribute to that code base from a whole variety of companies, not just from the prime contractor, but a variety of subs. And also, there's actually good government partnering and government interaction with that code base, which I think is one of the keys to success of good programs. Is government takes an ownership and is involved day to day on the Agile teams with the contractors. I think that kind of partnering is essential. That's where we see a lot of success. So, and another big difference, I think, is the level of required rigor for developmental test, operational test, which developmental test is really sort of verification. Did they build what I was supposed to build? Operational test is really validation. Is it fit for purpose? Is the thing that we built meet the mission requirements that we need? And then also the safety certification and flight testing and all of that other stuff. Anytime you build a system, especially a complex weapon system that yields deadly force, there's a huge responsibility there to make sure that it's safe and secure and high quality. So those, what have been referred to as tailgate processes, that I think diminishes the importance of them a little bit, but those end processes are necessary. And one of the big challenges we're having and seeing is, how do we integrate those? It's another term that's used often is shift left testing of it. How do we integrate those activities more into the DevOps cycle, the DevSecOps cycle? And and create confidence as early as we can during development so that those other processes at the end can be shortened, because we've got things like automated testing that we're never going to get away from sort of some level of developmental test, operational test, and safety certification flight test. We're never going to get away from that entirely. But I do think that we can develop ways or build confidence into the development tool chain so that those processes are shortened and we can move on more rapid iterations. And then also the big principle of DevOps, another big principle of Agile and DevOps is batch size. Decreasing batch size, if we reduce smaller changes more often, those things are also easier to certify. But then another challenge with that one is the legacy code bases we have in some cases, in many cases actually, don't lend themselves to isolation as well. So there's always a lot of the testing community will always say, if you touch one line of code, I got to retest the whole thing. In a good architecture and a good design, we ought to be able to implement those changes and localize their impact so that we maybe don't have to retest the whole thing or recertify the whole thing. And actually, that's the case in some other programs that are some other more modern programs that we've been working on. There's been very good architectural and design approaches that have helped localize, like the mission systems in the cockpit are completely segregated from the flight control systems. So if we make a change to the mission systems to be more responsive to an adversary threat, we don't necessarily have to recertify the flight control systems. So in some of our newer programs, those things that design architecture approach has been showing fruit so that we can move some of that certification and testing earlier in the life cycle.
Let me give you a little bit of an example. You might say, well, can you do incremental development with a focus on architecture? Can you do architecture incrementally? Let me tell you a very quick story. And this story is about the Mexican Stock Exchange. So the Mexican Stock Exchange approached the SEI, actually Bursatech, which is the technology arm of the Mexican Stock Exchange, was tasked with building a new trading engine, because the decision was made not to buy an off-the-shelf trading engine, but to replace the 3 that they had. And Bursatech committed to deliver this trading engine in a little more than 2 years. They asserted that it would be high performing. They wanted it to be a higher performing, in other words, faster than the previous engines they had, but they also wanted to be faster than their competitors, faster than NASDAQ, the London Stock Exchange. Such a system has to be highly reliable, as you would understand, and high quality, and it's got to be scalable because there are peaks and ebbs in stock trading, and the system has got to be able to withstand high loads in trading volume. So the SEI's role was a coach. We coached the Bursatech team, and we worked with the principles that we espouse, namely our architecture-centric engineering approaches, which you can read about, and also the team software process. And this is a familiar diagram that I showed you earlier about the role of architecture. And we wickered this with the various SEI architectural techniques. We used TSP as the scaffolding for team management, project management, and measuring. And I just want to show you very quickly some effort charts so that you see that architecture was actually spread across the 6 cycles of development that were used. In the beginning, we did architecture design, and we did some UML detailed design, and we did some prototyping. We needed to understand what was possible, and so the prototyping was important. We did very little requirement solicitation because we started out with basically replacing the engine systems, stock trading engine systems that actually existed. In the second cycle, there was much more of an architecture emphasis, much more requirements. We did a lot of coding in UML diagrams, and we did actually a skeleton of the system so that we could test out the communication between the various components in the architectural design. In the third cycle, we actually stubbed out the system, and we did a fair amount of performance testing, going end to end to see what the throughput could be. In the fourth cycle, We didn't actually keep effort metrics, but we used this to rethink garbage collection and collect some things that needed to be done. In the fifth, we actually had a day trading system, full functionality for day trading. We developed the testing framework, the testing, and we begin to admit the new requirements for the things that were to enhance this engine stock trading engine. And finally, in cycle 6, we delivered the complete system, which was not only the day trading, but the maintenance at night, the startup, the actual maintenance and logging that was done. There was still some architecture, still some requirements. If you add up all the effort overall, only 15% was spent on testing, which is very unusual for this type of system development. Now, let me give you the punchline. Was Versatech able to deliver on what they promised? Yes, actually, they were able to deliver ahead of time with hiring no increased staff. And I would add that many of the people we coached were not seasoned architects by any stretch of the imagination. What's really impressive is that the performance was 300 times faster than the actual performance of their earlier stock trading engine, faster than NASDAQ and faster than the London Stock Exchange. What I have here before you are numbers that are publicly available, but I know that the situation is actually even better than what's publicly available. And the quality, 0.1 bugs per case lock, which is very unusual. In this type of system, we would see 0.5 to 1. Since the system has been launched, there has only been one software problem, and it was easily remedied. So in fact, the architecture was developed incrementally. The quality of the system was delivered as expected, in fact, exceeded expectations. It was delivered on time, at cost, and we did it incrementally and used the architecture to perform the analysis that was necessary in order to deliver on the quality attribute agenda.
Good afternoon, everyone. My name is Ipek Özkaya. I'm the Technical Director of the Engineering Intelligent Software Systems Group at the SEI, and I will be your facilitator for our afternoon sessions. You've heard all different kinds of work that we do at the SEI, but one of the areas that we've been focusing on since actually our establishment is developing practices for software architecture. Software architecture is critical in ensuring that the systems are viable, they're developed timely, and they meet their business and mission goals. However, one of the other challenges that we see increasingly in the Department of Defense and industry alike is speed. How can we actually ensure that our systems are developed correctly, timely, and at a speed that can meet its customers' needs? And the big gap from that perspective is whether we can actually provide automation that is fit for its purpose. At the SEI, quite a number of our projects focus on how we can formalize some of the aspects of the software development process so that we can actually provide timely and correct automation that can meet some of these needs. We have different bodies of work that focus on this aspect. For example, the model-based engineering body of work that you will hear this afternoon looks into development of the architecture, analysis, and design language, and has been actually making significant impact in the Department of Defense and in the standards organizations. The part that is still a challenge for developers, however, is how we can provide support for more higher level abstractions. Like, for example, when you need to evolve software, do you still have the right tool support to be able to help you understand when you refactor the software, and what parts of the problem that you need to focus on. While we have quite a number of tools out there that come from industry and researchers alike that focus on helping us improve the quality of our software, that help us maybe even do small scale changes, they really do not address the larger scale software evolution that many of the DoD programs face, especially when we look into legacy software, reusing some of the capabilities going forward, upgrading technology, and being able to support the developers in the right way is still an open gap. So those are actually the kind of research challenges that we look into, and in collaboration with our partners, both in industry, academia, as well as DoD, we try to make strides in that. And those will be actually the talks that you will hear this afternoon. My colleagues, James Ivers, will focus on our automated refactoring assistant work, and my colleague, Jerome Hughes, will talk about the work that we're doing in TwinOps and using model-based engineering. Then actually we will come back and do a panel together. So please share your questions with us throughout their presentations so that we can address them, as well as during live in that session. And then we'll give a short break, which will be followed by our work and updates on the work that has been going on in the AADL. One of the things that I ask you all, we're in this unconventional mode of working from home, but we really appreciate the interactions. Please keep the questions coming. If we can't address it in the given time that we have, we will definitely get back to you from in our different channels, and we'll be happy to continue the conversation. Especially if you have a problem at hand that you think some of the approaches that we're showcasing can help, we're all ears and we're willing to work with you to the extent we can. With that, I think I will leave the stage, and we will start with James Ivers and go to the talks. Thank you very much, and I will be back with you after the talks. Thank you.
Hello. I'm James Ivers, and I'm here today to tell you about the Untangling the Knot research project. The essence of the knot is to build a prototype that helps organizations more quickly evolve their software in several common use cases. This project is in its second of 3 years, so along the way I'll show you some of the results that we've already achieved and some of the possible uses of the tool even today. The motivation for this project comes from two really pervasive observations in our experience. The first is that no significant system gets built today without software. It is just such an important building material for anything that we do, that our ability to work with software is truly important. It affects project cost, time to field, and so on and so forth. We also know from decades of successful work in software architecture here at the SEI that architecture can be a really good indicator of how easy software is to work with. Architectures that are well aligned with the needs of the software that we're working on, of course, account for rapid change and the ability to innovate quickly. Architectures that become misaligned with software tend to have the opposite effect. They can delay progress and in fact sometimes act as outright obstacles to making progress and making changes to software. The other really essential observation that we have is that good software is never done. A system that is successful will be used over and over again for years, if not decades. And over time, change is the real constant. We know that requirements will be added, business priorities will change, our technology landscape will change as we move software to new platforms we weren't thinking of 10 years ago. All of these changes are helped or hindered by how well the architecture of our software matches today's needs. And unfortunately, over time, the ideal design of a piece of software will drift from its actual design because we're asking it to do all kinds of things it was never intended to do. This growing gap can cause a lot of difficulties for organizations. It can mean software is very hard to change. It's error prone in terms of lots of defects are introduced when trying to change it. Or it's just very, very expensive to do things that should be very simple. Sometimes this is referred to as technical debt. Sometimes it's simply a change in purpose. Either way, in order to keep our software as an efficient building material, something that we can innovate in quickly, we need to periodically bridge this gap. We need to bring the architecture back in line with today's needs. And that means restructuring the software. And so that's where Untangling the Knot comes in. The status quo for how people restructure software today is through a practice called refactoring. Refactoring is very widely known in industry, but is largely a labor-intensive process through which a team of developers can have to sort through hundreds of thousands, if not millions of lines of code to figure out where changes are needed, and then sort through dozens of options for how to refactor the code and then realize all of those changes in code. What we're trying to do with Untangling the Knot is create an automated assistant that automates most of these labor-intensive activities. And if you look to the bottom here, at a black box perspective, we really require two inputs. We need the source code that we're trying to improve, and we need a notion of the kind of goal, the kind of refactoring and restructuring you're trying to achieve with that code. Given those two things, our goal is for our assistant to be able to accomplish those changes in code in less than a third of the time it would take through manual approaches. And to start this work, we have zeroed in on a really important recurring problem that we call feature isolation. You can think of this essentially as lots of different changes in software that require you to first take a piece of software and isolate it from the software around it. For example, if you're trying to containerize something or deploy it as an independent service in the cloud, you first have to decouple it to some degree from the things it was previously coupled to. That's the feature isolation problem that we're tackling with the Knot. So as a way to explain some of the use cases, I'm going to go through three categories of ways that it can be used and how it can help organizations at different points in their own decision cycle and at different points of maturity of the tool. The first we consider as an analysis activity. That is, there are lots of times where an organization wants to incorporate a new technology or interact with a new system. But doing so, they first have to do some basic activities. And a good example of this comes from an example from a government organization we worked with a couple of years ago. They wanted to take a successful capability from one platform and just use it on another. Conceptually, this sounds like a pretty simple idea. Take a good thing, use it somewhere else. Well, they asked their contractor, how much will it cost to do that? The contractor did their due diligence and they came back with an estimate of 14,000 development hours, 14,000, just to decouple it from its original context. And a very good question for anyone to ask is that a reasonable estimate? Well, the upfront portion of our refactoring assistant can help you answer that question. Because we take the source code in and we have a notion of a goal, for example, what is this capability you're trying to rehost to a new platform? We go through the analysis to generate lots of data that tells you what specific portions of code are affected by that change. So rather than basing a cost estimate on a simple notion like what's the total lines of code in the project, we can really narrow that down to the specific code that is affected by the goal you're trying to accomplish. And it gives you a lot of granularity in this kind of analysis. You can imagine doing a similar thing at a portfolio level. Certainly no program has the budget for all the modernization activities they would like to perform or all the innovation they'd like to enable. But by using this kind of analysis across the portfolio, you can quickly help rack and stack which of these are more feasible from a technical perspective because less effort is going to be required for those initial steps to isolate features. So this is a really important capability, and this really speaks to sort of a project management notion of how do I understand what I'm doing and what the implications are for a change that my technical teams want to do. But we also have help for our technical teams because as part of many modernization activities, there's a natural analysis of alternatives approach. Developers look at lots of different designs, they weigh the pros and cons against multiple criteria, and this is wonderful. What we think we can do with the Knot is we can add automation support for adding another criteria to that analysis. So take, for example, a common example today of breaking up legacy monolithic applications to deploy as services or microservices in the cloud. This involves a range of different decisions about how you take existing functionality and partition it across some number of services or microservices. With the Knot, what we can offer development teams is an ability to quickly sketch several different decompositions that they're considering and get that same analysis I talked about in the last slide, which tells you what's the relative difficulty of partitioning your software in one way versus another. So all of this really gives teams a way to solve their problems, to find the implications of a solution they're proposing to their system because they know what kinds of changes make a lot of sense. But the real power from the knot comes in the third category, and that is we want to go beyond, not just go beyond what are the impediments to change, what are the issues that are going to factor into that cost estimate, but we want to recommend a solution. And in fact, the prototype does that now and is growing in capability in this area. So essentially, think of it as I have the same scenario. There is this capability I want to isolate from its environment in one hardware platform so I can rehost it on another. What the automated refactoring in our tool does is it builds a model of the software and it searches for lots of different combinations of changes to the software, lots of different places in the code to refactor, lots of different refactorings to apply, and in lots of different orders. And because this is an automated thing, it can search for just a number of possibilities no development team would ever have the time to consider for themselves. And the output is a specific recommendation, which is very, very concrete. It is a specific set of steps of changes to the code in a language that engineers understand really well and can independently verify prior to applying to their code. So if you want to take this capability and put it in a container, it will give you a list of, say, these 60 steps are what you need to go through, and look for yourself, confirm this, and then implement it. So this is where the just tremendous opportunity is to save time. It's an option to explore many, many more solutions than development teams can explore manually, which will also hopefully lead to better solutions. The key concept behind this is framing this as an optimization problem. That's what allows us to turn search algorithms loose to look for solutions that we might have missed, or even to find those that we might have found much more efficiently. So if you take an arbitrary piece of code, we know there is structure in the code. It's not an undifferentiated mess. And so the illustration we have here is a small piece of open source software where we've applied some semantic knowledge to what the code is, what it means. Classes are this color, methods are this color, and there are different sorts of dependencies among all of these entities and relations. But to think about what it means to harvest a feature, to take it and move it somewhere else. Suppose that this portion of code in the upper left is what we want to isolate, what we want to harvest as a reusable feature. Well, we know from our knowledge as architects that not all data in this picture is relevant to that problem. And that's an important insight. It gives us tractability. We know, for example, that all the dependencies between code that's not part of that unit, they're not getting in the way of harvesting that piece of code. Relationships within this code, well, those really aren't all that important either because they're all going to the same new location together. What really, really matters are these red lines, which we call problematic couplings. They are dependencies from the code that we're harvesting to the code that won't be present in a new context. Each and every one of these couplings is a dependency that will break and a reason why that harvest operation will not be successfully completed. Because we can construct these graph representations from source code automatically, we can compute these relations very efficiently. We can enumerate each and every one of these problematic couplings, which feeds the analysis of where the problems are very specifically. And because this is countable, this gives us a basis for something called a fitness function, which is a way to compare one change to a graph to another change to determine which is better against that criteria. And that key insight allows us to turn search algorithms loose to find solutions that get rid of as many of these red lines as possible, therefore saving our developers tons and tons of time chasing down all those threads themselves in potentially very, very large code bases. So if we step back and look at this from an end user perspective, if we take a look at those first two scenarios where we're trying to analyze a problem and understand the difficulty of a change we're trying to make, we start with this source code, and we've tested our prototype on more than 1 million lines of source code. Given that source code and a little bit of help from a developer and a very simple way to identify what is the code that you're trying to isolate, once those two steps are given to us by a user, the rest can be done by our tool automatically. It can go through and enumerate, for example, in this 1 million line of code example, that there are more than 2,000 problematic couplings getting in the way. And we can report lots and lots of data. We can point to the lines of code on each end of every one of those dependencies. We can identify all the classes involved, all the methods of those classes that are involved. And we can distill that information into some pretty useful stuff. right? So from these 2,000 problematic couplings, we can determine that there are really only 144 unique targets just by lining up the names, something that a very simple analysis can do quickly. With just a little bit more work, we quickly determined that all of these things, like methods and properties, they're elements of classes. If we consolidate that information and just look for the unique classes, then with about 10 minutes of work using our tool, we go from a 1,000,000-line code problem to understanding that only these 24 classes are where we need to focus our attention. And that is tremendous advantage in terms of focusing developer attention on what matters instead of trying to figure out what matters. But as we step ahead to the refactoring end of the tool, we have the same precursor steps. We still need the source code. We still need the problem that we're trying to solve. But now we need to say a little bit more. We need to say something about the characteristics of the solution that are important to us. And I'll talk about this a little bit more in a couple of slides, but this comes down to identifying multiple objectives that we care about. Because we know as architects and software developers that a lot of what we do, the really hard stuff, is making trade-off decisions. I have to give a little performance here to get a little security there. We understand those changes. And as part of what we're doing, we're using a multi-objective genetic algorithm to search for solutions that give developers insights into those trade-offs and give them a range of solutions that reflect different balances of those trade-offs so that they can select a solution that meets their context as opposed to some just arbitrary best answer. So when using the tool, provide the same input, give us a little guidance on the objectives, and at the end of the day, pick a solution on the curve that matches your area of interest, your desired trade-offs, and the tool will give you a solution. And that solution looks like this on the left. It is a simple step-by-step process for how to refactor the code. It's very easy to follow because it uses a vocabulary that developers are familiar with. Moving a property, moving a class, moving a method, encapsulating a field. These are very familiar concepts, which makes it easy for developers to review. But we can also look at the data that goes along with this. In that case of the 1,000,000-line code project where we had 2,000 problematic couplings, we found a really interesting insight that after just the first 6 refactorings, more than 90% of the problem was solved. And so this gives developers that additional insight to know where the big wins are quickly so that they can focus on the easy stuff. And then maybe where the tool gets in diminishing returns, maybe they want to take over from the assistant and do the hard bit themselves because it's getting a little bit murkier. This notion of an automated assistant that gives you a partial answer allows that give and take with the developer. It gives them enough control to trust the answers and to understand everything that the tool is doing. And we believe that this will be a big asset in accepting the results and putting them into practice. But again, I want to say a little bit more about multiple criteria because this is very important to any real solution. At the end of the day, we have to generate solutions that developers will accept. And so to do that, we've been talking to developers to understand different criteria. And you'll see here a few examples of what those look like. There's the solution to the core isolation problem. This is minimizing problematic coupling. That's pretty obvious by now. But there are other things that developers care about. They want to minimize the work that they're going to have to do after the refactoring assistant is done. So one way to think about this is the more classes that we muck with, the more invasive the refactoring is. The more pieces of code might have to go back through code inspection or might have to have unit tests rewritten. So there are ways to use different criteria to minimize those sorts of invasive changes. We can also look at typical code quality metrics to make sure that we have a more maintainable result when we're done, that code is understandable, and that we're not introducing vulnerabilities by overexposing the information available in our APIs. There's a range of these things that we're looking at to understand from a qualitative perspective, what do developers care about? But on the back end, we marry this with good old statistical analysis to make sure that all of those different functions that we're looking at are actually measuring different underlying phenomena. And while you can't read the individual labels on any of these particular fitness functions, each fitness function being a measure for one objective, you can see that some correlate really highly and you're maybe not really measuring such different things. And so we're doing this kind of analysis both on the front end by talking with developers and on the back end by running the data to see what is that good compromise. What are the good fitness functions that differentiate solutions for us, get us more of that trade-off space without wasting a lot of computational time, because the more objectives we add to search, the more computationally expensive it can get. But at the end of the day, we get this notion of a range of solutions that are good for developers. And this relies on a notion called Pareto optimality. Essentially, what this means is that if we look at a two objective solution, in this case, problematic couplings and lines of code. In this case, we're really trying to minimize both measures, right? We're trying to get down towards the origin as being the best possible solution, right? The best possible solution in this case would solve all the problematic couplings without adding a single line of code. It's unrealistic, but we can dream. But what we see is that as we run the search, Pareto optimality collects a range of solutions that don't clearly dominate each other. They reflect that give and take that developers understand from the trade-off space. We have a range of solutions at this end of the spectrum that really solve most of the problematic couplings, but at the cost of adding more code. At the opposite end, we've got solutions that add very, very little code to the original feature, but they don't solve a whole lot of the problem. We have compromise solutions in the middle. And this really gives us an ability to talk to developers in their language, to understand their context and give them some choice about which of these solutions to look at. And that's really important. But behind the scenes, I'm afraid I don't have time in today's talk to go into this as much as I would love to. We're in the realm of meta-heuristics. Genetic algorithms have a whole bunch of parameters that we can tune to get to better solutions, to converge to solutions more quickly. And we are running thousands and thousands of experiments behind the scenes to tune these parameters to solve this sort of problem across a range of different code bases. And this illustration is a simple one. Again, the axis here is problematic couplings. Fewer are better. What we're varying here is a very straightforward parameter. How many generations are we running through that genetic algorithm? These are the iterations of search, right? And so the fewer iterations have less reduction in problematic coupling. The more we run, the better our solutions are and the more they converge towards better solutions. This is not a terribly significant or surprising result, but we're doing this across all of these parameters to tune the algorithm to the nature of the problem that we have because it has its own intrinsic characteristics. But let me step back and say where we are right now. As I said earlier, we're at the end of year 2, and so we've got a working prototype that we can apply today to C# code bases to solve those first two categories of scenarios that I talked about. We'd say those are TRL4 capability. The automating refactoring is not falling far behind. We're currently in trials where we are comparing the results of manually refactored code to what the tool recommends in getting expert developers to give us their feedback on the tool to help us hone the algorithm, hone those fitness functions, and generate better and better solutions. We're expecting that portion of the tool to be at the TRL pilot ready phase in maybe 3 to 6 months. And so this is really encouraging. We have working code, we're happy to solve problems, and we are eagerly looking for partners to try this on. Our prerequisites are pretty simple. We need source code, and we need a semantic idea of what you're trying to accomplish. What's the feature you're trying to reuse or package or in a container or something like that. Right now, everything is targeting C# code bases, which we've tested up to about 1.2 million lines of code. But Java capability is not that far behind. And so if that's your working environment, please reach out to us anyway, because I think we have some potential there to engage. But stepping way back, this is part of the SEI vision to really improve the automation that's available to architects and designers and developers, and to tackle these really significant problems that tend to be addressed manually today. Right? I talked earlier about the gap that tends to emerge between the software that we have and the structure we really like. What the knot really is this drastic, efficient intervention to bring those more in line very quickly. And this is part of our efforts to use AI to solve software engineering problems and really improve the capability that development teams have so they can focus more on innovation than refactoring code. And if this is of interest to you, please reach out, and thank you very much for listening today.
Hi, my name is Jerome Hug. I am the PI of the TwinOps project, a one-year exploratory project funded by the SEI during FY20. TwinOps aims to address the challenges in building cyber-physical systems. We know that cyber-physical systems still exhibit misbehaviors after field test. What we observe is that their engineering relies on models built in isolation, limiting in-depth unit and integration testing until the system is done. In this project, we are combining DevOps and model-based engineering to ease the construction and deployment of systems, their simulation test benches, and digital twins. TwinOps combines system models, software models, and physical models to improve system understandings. TwinOps builds on the expertise of my team working on model-based engineering. The MBE team within the SEI improves the state of the art and influences the state of practice to build safety-critical systems faster and with confidence. Our vision is to leverage models to create the best design that will hold up over time as the system evolves. Test the design in all its dimensions, functional, timing, performance, security, or safety, using state-of-the-art technologies as early as possible, even before the software is actually written. This is made possible by defining a high-level modeling language that combines hardware and software concerns and allows to reason on the architecture core quality attributes. To achieve this vision, the SEI has been developing two core technologies to support it. First, the SEI Architecture and Analysis Design Language, or AADL. AADL is a domain-specific modeling language for modeling safety-critical systems, merging both software and hardware concerns and populated with a large set of properties to finely tune the system. This language is supported by many tools, including SEI Hosate toolset that supports model editing and analysis capabilities. Both technologies are increasing in maturity through multiple case studies for the US Army and its partners. We are strong advocates of model-centric approaches and of the AADL language, but we do acknowledge that AADL is not the only language when it comes to design cyber-physical system. Let us consider the case of a basic UAV. Its architecture could leverage more precise models for specific engineering steps. For instance, symbolic models that define its control laws. In addition to those models, we may use AADL for the embedded system architectures and define the core attribute of the software prior to implementing it. In addition to that, because we want to build a CPS, we will need a CAD model for the mechanics. Ultimately, all these models are integrated to build the system. However, what we note is that those models are built in isolation, which means that, as part of the integration test, what we may discover is that some specific hazard or threat, for instance considering safety, were not properly captured and mitigated by the AADL level because they come from actual sources from the CAD models that were not available at that time. Indeed, such issues such as sensor timing jitter, bias, imprecise component behaviors in both the functional or safety domains are still discovered late during testing or even after the system has been deployed. Recent incidents like the Boeing 737 MAX MCAS issues or autonomous vehicle incidents have all in common an imprecise characterization of the interface between cyber and physics. This leads to subtle bugs in time-sensitive control, detection and handling of exceptional conditions. Additional sources of truth exist, and actually all those models that have been built exist and participate in this single source of truth of the system. Each of them exhibit more precise behavior or specific misbehavior when it comes to safety that will have a deep impact on the engineering, and those should be considered. And this is exactly one of the key objectives of TwinOps, leveraging all those models so that we can use more precise models instead of naive abstractions when it comes to validation and verification. Ultimately, we want to combine all those models, all those domains, including system engineering, to improve on the engineering of cyber-physical systems. That being said, and before we go into the definition of TwinOps, let us do a technology focus on model-based techniques. Models, generally speaking, are abstractions that address specific concerns, One can say, by analogy to various worlds, that models are nothing but static and dynamic architectures. A review of modeling techniques reinforces this view with different types of models. For instance, SysML package or block definition diagrams are basic static architecture definition, and they are rather informal in that they convey very little semantics on the actual system. SysML activity or sequence diagrams are defining the behavior of the system at a very high level, yet they are usually not amenable to formal analysis like model checking. On the other hand, languages like AADL, Simulink, Modelica, each in their specific domains, bring sufficient semantics to enable rich analysis, model checking, performance analysis, or simulation. We can go even further and consider what we can do with models. Models are usually considered as a way to document a system or to run some analysis. Actually, we can go much beyond and actually generate code from some variety of models. For instance, one can generate code from models ready to be embedded in the system, for instance from AADL to C, from Simulink to C, and get insights from the system by generating software probes and exercising the generated system. We can also generate code so that we can simulate models and generate simulation code as a mock-up of some system parts. This is possible, for instance, using Modelica or Simulink, so that you can simulate the environment of your system. Finally, by combining those two approaches, we may imagine building digital twins. Digital twins allow us to compare the actual systems and its digital doppelganger that lives in the simulated world. By comparing the two, we may assess the system as it is running and do prognosis or diagnosis on the system. Those various model processing capabilities are at the core of the TwinOps project. And now we can introduce TwinOps step by step. The first aspect of it is that we mentioned that TwinOps relies on DevOps and code generation. However, DevOps is a software engineering process, not really a model-based one. Indeed, DevOps aims to create a virtuous circle for software quality, combining development, V&V, deployment, and monitoring in a unified workflow. DevOps is relying on a specific IT infrastructure, offering source configuration management, continuous integration, continuous deployment, using containers and IT microservices. From those premises, what we can do is define what is mod DevOps. The general intuition behind mod DevOps is to extend DevOps capabilities. Model can enrich development activities by producing requirements developers must implement, but they can also provide evidences that those requirements are sound. For instance, the dimensioning has been correctly performed. And in addition to that, reduce some of the development activities by generating code from models. Similarly, operation or ops activities may provide more precise metrics, for instance on timing or resource consumption, that may inform the next iteration in model construction, improving both the model side and the development side of the system. As we define it, mod DevOps aims to define a system software co-engineering culture, something that is similar to DevOps by considering also models as central artifacts. Mod DevOps is built on the idea that model-based engineering is a natural extension or complement to software engineering. By providing machine processable models, we can increase automation to improve system V&V through code generation, through analysis, and through automation of those activities. Let us take an example to illustrate mod DevOps in action, so that ultimately we can define what TwinOps is. Let us consider UAV, which is a canonical cyber-physical system. What can, for instance, first use SysML to capture its core mission, stakeholders and key parameters and architecture. From this model, we can derive a controller and a hardware software architecture that supports it. The controller could be implemented using Simulink, hardware software using AADL. Let us note these models complement each other. Simulink will define the computation to be executed, and AADL, how those computations are actually executed and how they will use specific sensors or actuators to fulfill the mission. Let us note that each model is first validated in isolation, but they can also be combined so that, for instance, performance analysis of AADL will inform on the controller of whether some performance metrics can be achieved. Finally, a SEI implementation will be derived and, together with the AADL model, be deployed on the UAV. From that particular aspect, we can actually derive what is nothing but a model-to-code pipeline. We can leverage AADL to SEI code generation, we can leverage Simulink to SEI code generation, compile the code and deploy it directly. So through code generation, we can reduce many manual activities. And basically here what we are demonstrating is how mod DevOps extend DevOps by using not only software programming language as inputs, but also models. Of course, we can extend this pipeline to execute all type of model analysis prior to allow the code generation process. Now that we have introduced this first process, we can go further. Again, using this UAV as an example, we may complement the set of models we're using. And for instance, in addition to the model of the UAV itself, also add a model of the plant, of the environment that will be the theater of operation for the system. For that, we can use Modelica. Modelica is a language for defining precisely the physical components of a system. It supports an acausal, equation-driven way of capturing the mechanical aspects of a system. Modelica supports model simulation and also model compilation compatible with the functional mockup interface standard. The interesting aspect of this functional mockup interface standard, or FMI, is to allow for the direct coupling between all those models. By providing simulation capabilities, we can define all types of pipelines. For instance, co-simulation of the controller in Simulink and of the plant in Modelica, so that we can go further in validating the controller. Those various combinations allows for all types of cross-validation using the variety of models provided. For instance, we can validate the controller in the plant using FMI. We can validate the Simulink model combining the AADL and SEI code, and we can also perform virtual integration by running a mockup of the system using the environment, using a simulation, of the environment provided by Modelica. Let us illustrate this later scenario. So in the second pipeline, we add new steps. We have the Modelica model that we can compile into an FMU, and we can combine it with the AADL model. From that part, we can execute the previous model to code. This pipeline is actually a variant of the previous pipeline. We can actually have two options for deploying the system. Using the first model to code pipeline, what we'll do is that we'll actually use the device driver code to read from the sensors or act on the propellers. In the second pipeline, what we do actually is that we build a simulation of the system, and instead of using the actual device driver code, what we will do is we will interface the functional mockup unit generated from Modelica to simulate sensor reading or simulate the action of propellers on the environment. The second pipeline allows system engineers to analyze precisely their system as they conceive it and perform all types of mission validation in a purely simulated and controlled environment by tuning the Modelica model. Here, what we have done is basically define two pipelines. Those pipelines are independent from the model itself, and from that, systems engineers may decide in which order they will execute or evaluate them. You may decide to go directly to code and do some rapid system prototyping and deploy on the target, or you can decide to do many simulations waiting for the actual platform to be ready. Those pipelines are just one of the many combinations that we can perform. Another one is simply to consider that we have those two pipelines and we can automate also the deployment of the software. So here we'll take the source configuration management system, execute the model to code pipeline, and use a deployment over the cloud, for instance, Azure IoT directly on the target. This pipeline gives us the opportunity to deploy systems directly from models. And here, basically, what we are doing is executing a continuous integration, continuous deployment system from models directly to deployment on the UAV system. We may also execute the model to simulation pipeline that we have defined before, and ultimately create a digital twin of the system. This digital twin is taking advantage of all the models that have been created and will allow us to run the system. By combining those two pipelines, what we achieve is actually a complete closed-loop system engineering process, from model to deployment, from model to simulation, from co-execution of the system and its digital twins, so that we can consolidate many engineering data. Those engineering data can be compared in real time for diagnosis, but they can be also compared after the execution of system, allowing for precise re-engineering step or incremental improvement over the system. Those various capabilities are just one of the few scenarios that we can define around this idea of mod DevOps, pipelines, and digital twins. As we defined it, this mod DevOps and digital twins, or TwinOps as we call it, is extending the general idea of DevOps by defining a model DevOps cycle. First, we will plan for the requirements and properties of system and model the architecture and parts of our system. Then we'll perform virtual integration. That is, basically, we'll perform verification and validation at model level to evaluate the feasibility of implementing the system. Then we will perform code generation and deployment of the system. This relies on automation capabilities or code generation from model to code and from typical DevOps practices of continuous integration, continuous deployment, and deployment over the cloud. From that, we can either run the system or simulate it, or do the two in parallel, like a digital twin. Finally, when this is done, we can collect data, monitor specific assets, specific attributes of the system that we want to collect, so that ultimately we may analyze them to infer any system updates that will be relevant. From all those facets of the project, what we are delivering through TwinOps is twofold. First, we introduce mod DevOps as an innovative approach to bridge model-based system engineering and software engineering through DevOps concepts. Mod DevOps pipelines allows for a smooth transitioning from model-level validation and verification to software production using code generation from models. Then, we have presented TwinOps, a specific mod DevOps instance that equips systems engineers with new analysis capabilities through the careful combination of models artifacts as they are built. TwinOps builds on the SEI expertise in DevOps and model-based engineering, and actually reuses many existing tools and combines them through those mod DevOps pipelines. Future work will address the precise modeling analytics pipeline to improve the understanding of the system, from the definition of the modeling artifacts to monitor, to the logic to implement them, the actual monitoring and data processing aspects. Thanks for attending this presentation. If you have any questions about this talk, you can contact us at the following address or attend the following Q&A session. Thank you.
Okay. Hello, everyone again. My name is and I'm here with my colleagues who just presented, James Ivers and Jerome Hughes. There's a question that I see in the chat that talks about, it asks where the presentations are. At the end of each day, you get links to the presentations and they will be available at our digital library. The presentations that's going on today are not there yet, but by tomorrow you'll be able to stream that. With that, let's get started with the questions. I see one from Patty. Jerome, I think this is for you. And the question is, what is the average time frame for modeling the environment steps? So since you just presented, let's start with that because it's new and fresh in our audience's mind.
Yeah, sure. Thank you, Ipek. And thank you, Patty, for your question. I guess the question that you're asking is probably related to more generally, what is the process you want to enforce? By time frame, I understand that in two different ways. When do you need to model the environment? And I will say at any time where you need that input for one engineering step. Is it for system engineering? Is it for simulation? It's part of your project description. The other question is what type of information do you need to build this environment? And that is related to some general question about mod DevOps, which is what type of inputs or what type of information do you want to get from that? So I will say in terms of time to build this environment, this model of the environment, it is as much time as you want until you achieve a sufficient level of accuracy, a sufficient level of precision, so that this model of the environment is good enough for all the information you want to extract. Should it be for testing, for simulation, but also for dimensioning your system. And so depending on the type of system, you will have to discuss with system engineers, with practitioners to see what type of information this model can provide and when to insert it into your modeling process. It's a very tricky question that relies on a lot of expertise across all domains, not just software, not just system, but also mechanical or physical. So I'm sorry, no definite answer, but really a discussion across all teams.
So thanks, Jerome. Maybe that's, I will follow up with another question kind of related to it, building on top of that. You mentioned that you use Simulink models because there are multiple aspects of different cyber physical systems that not one model is always fit for. Clearly, you need the combination of these models, but what are some of the challenges lying ahead in terms of being able to use multiple models seamlessly together? And what are some of the efforts that are ongoing either at the SEI or other places that move us forward towards achieving that?
Yes, thanks for the question. It's a very large question, a large topic. I would say the key research challenges, and it means that really in the broadest academic sense, is first off, if you want to combine models, you will need to think about the semantics of those models. Some will have continuous time, some will have discrete time, and how to combine all of that is really a tricky open challenge. So I would say from a pragmatic point of view, I would say the answer is make sure that you use each subset of those modeling languages so that you have a clear understanding of the semantics of them. Time is one issue, and when you consider continuous time or discrete time, you may have instantaneous time, and it's a large topic within the cyber physical system community. And do we work on that directly on the SEI? It's really at the borderline of what we're doing for the Assuring Cyber Physical System Directorate, but it's really part of the key questions that we want to address in the coming years because it's really a large question. We want to combine models because we know that we need that, but now we have to define precisely how to do that safely and with confidence.
Okay, thank you. And with that, I will move to a topic that is probably relevant to both aspects of this, which is developer acceptance. And I will ask this to both Jerome and James, but I will start with James. Part of the challenge that we see on and on related to these new automation environments is whether developers are accepting the new automation and new features, and whether they're able to actually trust the results, both from a perspective of the outcomes as well as the recommendations that go along the way. So James, let's start with you. What are some of the steps that we can take so that the developers can, in fact, accept the recommendations driven, as well as the new approaches? And Jerome, I will come back to you after James answers, because I think there's a relevant aspect of the model-based engineering aspects as well.
Sure. So I think
the starting point for me is to recognize that for a developer to accept a result from a tool, there's at least two kinds of questions they're typically interested in. One is the answer correct? And the other is, does the answer qualitatively match the direction they're looking for? And to make that concrete, in the refactoring research that we're doing, there are lots of correct answers that will reduce coupling in a system and isolate a piece of software. But they differ in their qualities, much the way different architectures differ with respect to different quality attributes, right? One might be a lower latency solution, another might be more maintainable solution. And so when we look for developer acceptance of these recommendations, we have to understand their preferences and ideally give them some feedback mechanism to help tune the answer. On the correctness side, however, we take more of an approach of making the solution very visible, very auditable, right? By telling the developer step by step, here's the things that are happening, so they can independently look and examine the semantics and not just have to blindly trust the tool because we're changing code without them, but to have that transparency to see what's happening and be able to ask questions and think through in a granular step themselves to confirm that they're okay with that answer. So to some extent, exposing transparently the correctness side of things, preferably in a granular way that's easy to digest, but also taking into account the varying preferences that we know developers have and finding ways to accommodate that in different contexts.
Thank you. And that also goes into how can I actually link the recommendations into end-to-end aspects of the downstream as well as upstream activities. I think the same applies to model-based engineering related approaches. Jerome, what are some of the challenges lying ahead and what are some of the steps that to take so that developers are comfortable with embracing model-based software engineering approaches, as well as some of the combination of modeling techniques that are out there that are available and upcoming?
Yeah, so I would say model-based is a big shift in terms of systems engineering. Should it be software or system engineering as a whole? One aspect is that you are turning all type of documents, all type of knowledge into a collection of models. So the first question usually through that is, first of all, is my model accurate enough for my objective? And so that's a really critical part because in the previous time when people were designing their system, it was a human activity with a lot of discussion, and so there were a common understanding. But now we are transferring this understanding into a model so that a tool can process it. And so the first key question is my model complete enough for a specific design objective? And it's not really an easy question. There's a lot of issues behind that. We discuss semantics, but it's also a regular concern in software engineering. I mean, there's still this joke about when do you stop requirement engineering and when do you start architecting your system? And it is still an open question. The second one related to validation or verification or model processing is what type of feedback do you get? So James explained already this idea of explainability of the results that you get through automation. And so for me, it is really asking the question of what does it mean to do IV and V, independent validation and verification? For some systems, a safety critical system, you really want to have a split between the people who design and the people who do the IV and V. When you interact with the MBE tool, you are really in that particular situation where some of the engineering, for instance, when you perform code generation, is done by a black box. You send requirements, which are basically your model, and you get a software. And so the question is how to do this type of IV and V, where instead of humans, instead of subcontractors, you have a machine. And it is asking a very interesting question in terms of how to interact. And again, it's really a fascinating research challenge because we know that we need automation, but now we need to trust that automation. Whether that automation is provided by AI or not is not even the question. It's how to trust automation as a general philosophy when we design our systems.
And that's actually where both of these pieces of work, as well as others that we're featuring throughout the week, is the formalisms help, because formalisms help to get to a more accurate answer, and you can actually know what you were able to answer and what you have not been able to answer. And that's actually part of the overall approach. So in moving forward, I think this is where I'm going to come clean with the audience. My systems are failing left and right. I know questions are coming, so I will have to rely on my colleagues, James and Jerome. If there's audience questions that we should be addressing, we should pick them up. So I know a couple of those are moving along, but I'm not able to see them. So are there any that came our way that we should address, or we can continue with our plan?
Yeah, so actually there are two regarding my presentation and one for James, so that will come in shortly. So let me start with probably mine, just to be, because they are the first in the queue. So lessons learned regarding providing feedback into the model derived from testing on real hardware. That question depends really on some ongoing work that is currently being done for some SEI customer. So it's not really something that I can discuss. So feel free to reach out to SEI, to info@SEI if you want to have more details about that. The second question was on FMI simulation that we're using for TwinOps. FMI allows you to combine multiple model of times. However, you have to know in advance whether this composition makes sense. FMI is simply a middleware. It will not solve the semantics issue I was presenting before. Basically, FMI, you can just view it as a gluing technology. So if the semantics is not correct, FMI will not detect it and will not report it.
Okay.
Then, James, there is one question for you that I will read. Is can you move from the model of interactions and change to prediction of performance, of safety, of latency? I mean, basically, does it scale to non-functional attributes?
Well, so that's an interesting question because non-functional attributes or quality attributes span a lot of different concerns. The concerns we're tackling with the NOT are typically things that aren't measured at runtime, like modifiability. The others that Bruce mentions, performance, safety, latency, these tend to be things you would measure more at runtime. And you can think of these as not quite partitioning, but related concerns that actually build on very different models usually. So the semantics and the computational model for your underlying analysis are going to tell you what you can reason about effectively. Our starting point with the refactoring work is to focus on those non-runtime measures. How easy is it to maintain the code, to port the code to a new platform, that sort of thing. And so that lends itself to models that have structural sorts of dependencies and that kind of information, more than information like execution time. It's quite possible to combine these models and add information. And that's one of the things that we're thinking about as future work for refactoring, is to add some notion, for example, of common execution paths so that you can penalize solutions that would add latency to frequently executed paths. But really, I mean, I think this is probably true of all of our work at the SEI. The particular computational models we use for any given model will lend themselves to some kind of analysis. And one of the tricky questions that's been a challenge for years is how do you bridge the gap between different kinds of models so that you can reason consistently across these different domains. And there's a little work that we've done there that's pretty encouraging, but it's a big challenge because computational models go beyond just continuous time, discrete time sorts of things into things that have nothing to do with time.
So I'll actually pick up on that, James, because one of the other kinds of work that we've seen is there's quite some work that focuses on, okay, I'll look into the dependencies of the code base. I will improve them because it will improve my modifiability, maintainability going forward. I think what you presented actually provides a shift in terms of how to approach these kinds of dependency correction or improvements. Can you say a little bit about how search-based algorithms and refactoring and our approach actually helps make that trade-off?
Sure. Yeah, that's interesting. So there's a lot of really good work out there on search-based refactoring that looks to improve general code quality metrics, things like coupling, cohesion, some of the QMU metrics. There's really a very different starting point from that work and the work that we're doing. The existing work out there in the research really is good at making general improvements, but it's done without any particular kind of lens, any particular motivation that this is the piece of code that I care about. In our work, we started from a very problem-driven or problem-focused solution. That is, a user tells us, this is the capability that I want to make or turn into a reusable component. That is essentially a constraint on the problem, but it also focuses the solution as something that's much more immediately practicable to a program office or a contractor or any organization who's really trying to get value out of that software, as opposed to scattered changes throughout a code base. both pieces of work are valuable, but it really comes back to the question of what are you trying to improve and why?
Yeah, focusing the problem into the relevant evolution and improvement, both with model-based engineering as well as search-based refactoring, I think at the heart of the advances that we're trying to go after. With that, maybe I'll ask a general question to you both, and you can take turns. So there's all this automation theme that we've been working on and formalization, but there are definitely open research questions out there in terms of DoD adoption. So what would be the open questions and the most important ones that we think we should be working on in order to move these technologies closer to adoption in the near future? James, you want to get started?
Sure. So honestly, the first questions that I think about aren't technical. So the questions that I think about for a program office is, what are you trying to improve? What's the change you're trying to make? And how can you make that a fairly specific thing so that we can measure for improvement? The second thing that is unfortunately still an issue for some programs because of legacy contracts is access to the data that you need to actually do the analysis, right? In our case, we look at source code. So if a program doesn't have source code, that's a huge barrier. Given those two things, we have research that can move in that direction. And from the research perspective, the things that we need to add are support for the right languages that are used in practice. We know there's a lot of variation in that space. Incorporation of the right semantics. For example, do we add more information about latency to make sure that we refactor in a way that respects not just modifiability, but performance? But really there's a synergy here between what are the concerns that matter, what's the problem we're trying to solve, what's the information that we need, and do we have the access to it? And given that, there's a lot of good research to build on in terms of the computational models that let us do the appropriate reasoning. But there's still work to do to pull that through.
I do agree that there are technical challenges as well as organizational and adoption challenges. Jerome, is there anything else you want to add to that?
Yeah, probably just one. James mentioned the impact on the program offices, and that's especially true for MBE. What we want is do a shift left, which is basically spend more time on modeling activities, on early integration. We really believe in that approach. However, it will change the balance of powers or the balance of budgets between activities. And basically, we have to convince program managers that we want to take more money at the very beginning to improve the system or to do improvement earlier in the system. And we know that it will come at some benefits that we can quantify. But for a particular program manager, it means that eventually we'll have less money for late corrective actions that we want to avoid. Mm-hmm. And this is a big shift. We understand that it is a risk-taking shift for DoD program managers, but we really believe that it is the right shift that we would like to support and to enable through our activities and research.
Mm-hmm. And I think it's the common theme that we have shift left with improved automation and improved formalism so that you understand what is the missing information and what you actually still have to supplement so that you can go through the different tasks accordingly. So I know there are questions coming on, but we're out of time. And I thank you all for your patience as we navigate technology as well as we navigated this platform. But we will see and address the questions offline if we're able to. As I said in the beginning, the presentations will be available for streaming tomorrow on our digital library. We'll give a 5-minute break now, and then our colleague Sam Proctor will be on talking about our work in AADL, and then we'll come back again with Jerome and Sam and have another short panel session. Thank you both, James and Jerome, and thank you all for the audience, and we'll all be back in 5 minutes.
The SEI is leading a national initiative to ensure that our nation's AI capabilities are built, operated, and evolved well. AI is already transforming DoD missions by helping human users go further than ever before. As we develop new AI capabilities, AI engineering can provide the roadmap to repeat our successes in designing models and algorithms, to integrate AI components into systems where they need to work with traditional software, to manage data and our computational resources, and to define the processes and policies that center ethics, mitigate bias, and uphold the trust of human users. Join the movement towards scalable, robust and secure, and human-centered AI.
Hi, my name is Sam Proctor. I am the initiative lead for the model-based engineering group here at the Software Engineering Institute. Today, I'm going to be talking about how the Architecture Analysis and Design Language, or AADL, helps us transition research ideas into practice. So this is a roadmap of where we're going today. We're going to be talking about the problem space that I work in, how AADL helps my teammates and I solve those problems. The DoD's recognized that, and we have seen some success in DoD projects. And then we'll wrap up by talking about how AADL aligns with DoD's digital engineering strategy. So let's talk about safety critical embedded software systems, which is sort of a mouthful, but these are basically cyber physical systems that, if they fail, are going to cause some sort of unacceptable loss. So think medical devices, aviation, certain automotive components, things that might cause a mission failure or an unacceptable amount of money to be lost, or even injury or death to a human if they go wrong. These systems are built in such a way that often issues are created sort of early on and caught later on. So issues are created in the requirements phase or when components are being designed, but then those issues aren't discovered until the requirement or until the components are actually integrated together or the requirements are being tested. So the idea is to discover system level issues early by annotating components and then virtually integrating those components. Our solution has two prongs to it. We have a language, AADL, which is internationally standardized. So it's not something that we've just come up with in a research project and are going to abandon. It has over 15 years of use in academia and in industry. Then at the SEI, we also developed tooling to support that language. We created an integrated development environment called OSATE, or the Open Source Architecture Tool Environment, OSATE. And OSATE helps system designers write AADL, and then once you have an AADL model, helps them analyze it for various system level things. So you can attach component level latencies to your individual components and come up with an end-to-end latency once you have the system specified. So I'm generally uncomfortable talking about AADL without giving at least a flavor of it. So first we're going to give a short overview of AADL itself. AADL has two syntaxes, a graphical and a textual one. And the graphical syntax is what we're going to be using in these slides, though if you're a computer scientist like me, you might find the textual one, which is declarative in nature, a little bit more comfortable. Its graphical syntax, though, presents boxes and lines, just like engineers are drawing on whiteboards all around the world. The difference between the boxes that AADL lets you draw and those that are drawn on a whiteboard is that the semantics are precisely specified for AADL. Using mathematical descriptions, we know exactly what they mean. So, for example, this box on the slide now is a temperature control process that might be used in something like a smart building to keep a room at a comfortable temperature using a computer to govern whether or not we need to turn on a fan. As a process, it is a protected region of memory, and we can allocate threads there. Now, it's likely that if you were just drawing this on a whiteboard, you could say all of that if you were well versed in system design issues. But what's the likelihood that someone looking at the whiteboard later on would come up with the exact same definition of a process that you would? Maybe not as high as we would hope. So that's the importance of standardizing the precise specifications of meaning that AADL enables. So we can put some threads in our process, something for a temperature sensor, a thermometer, something for a controller, a little bit of computational logic to say if the temperature is out of bounds or not, we should turn on a fan or not. And I promised you some lines, so now we can draw lines between those boxes. We can connect these threads, in this case, together with different types of intra-process communication, but we need to differentiate some of the behavior of our threads. This is where we can use AADL's extensible property mechanism, which lets us specify additional semantics to attach to various components and connections. AADL comes with a number of properties, but if you find that there aren't enough, it's easy to come up with your own properties and then use those to guide additional system analyses or code generation. In this case, we'll talk about the dispatch semantics and how those would be added with a property. Our temperature sensor is a thread that should wake up periodically and check if our room in our smart building is at a comfortable temperature. It will forward that temperature to the controller, which can decide whether or not, according to some configuration, that temperature is acceptable or not. If it is acceptable, then we don't need to do anything, but if it's not acceptable, we can turn on the fan. So what's key here is the temperature sensor needs to have what we call periodic dispatch semantics. That is, that the sensor should check according to some clock. Every once in a while, without any external interaction, it should just check the temperature. The fan, however, should only be turned on or off when the controller says it should be turned on or off. That is, using sporadic dispatch semantics. If we were to use periodic semantics for the fan, we would have a problem because the fan would turn on and off at the same rate, whether it was a hot day or a cold day, and our room probably wouldn't be very comfortable. So it's this sort of notion that we need to embed, and we can do that using AADL and the property specification mechanism. So that is the world's quickest overview of AADL, but I hope that it gives sort of a flavor for the language, because now we're going to shift gears a little bit and talk about how AADL helps us solve problems, how we use those formal specifications of developer intent to learn system level things, having annotated only the components in a system. So I'm one of the PIs on the Integrated Safety and Security Engineering Project, also called ISEE, and like the overall approach that we take in the Model-Based Engineering Initiative, we have a two-pronged solution here with tooling and language extensions. These are some of the high-level tasks that we did as part of the ISEE project. You can see that there are several of them, mostly tooling extensions, but also some modifications to AADL itself, like a new annex to the core language that lets system designers annotate their security requirements and how their system is going to go ahead and meet those requirements. But we can also talk about the various tooling aspects. Some of these are pretty stable, like descriptions of the library of error models that we have. The error model v2 library there on the left is maybe one of the more stable tooling artifacts that was produced as part of the ISEE project. On the other end is the architecture supported audit processor, which is, or ASAP, which is very much a prototype, but we think is a really exciting concept for the future of hazard analysis. So these different tasks, unfortunately, I don't have time to go into in great detail, but just to give a flavor of the type of work being done in this project, we can talk about the safety patterns. So the safety patterns task was headed up by a colleague of mine named Jerome Hugh. And the idea here is that there are a number of safety patterns that have been published in the literature, things that you should do if you want certain safety characteristics in your system architecture. So for example, if you want some part of your system to be immune to a single point of failure, you might use what's called the triple modular redundancy pattern, where you have 3 sensors and they vote. So if one of the sensors fails, the other 2 can outvote it and you'll still have correct sensor data. Unfortunately, achieving triple modular redundancy is not as straightforward as just getting 3 sensors and hooking them all together. You have to be pretty careful about how everything is configured, or you can still be vulnerable to a single point of failure. So what Jerome did was, using previous research projects, or the output of a previous research project called Architecture-Led System Assurance, he actually specified how triple modular redundancy architecture should look in AADL. And then those AADL models were embedded using an example mechanism into OSATE, the open source architecture tool environment, or SEI tooling for AADL. So now if you download OSATE, you can get the safety patterns shipped with it. That's available right now. Other research projects previously studied how to model errors in your system. That's the EMV2, and this was not done as part of ICE, but rather we built on it in this project. That's actually sort of a theme that I want to highlight, is that there has been a history of architecturally integrated safety and security work that has been done here at the SEI and then embedded into AADL and OSATE. So as you can see, in 2006, which is shortly after the original version of AADL was published, we noticed that users wanted to extend the notion of their component interface to include what we call off-nominal or rainy day behaviors. The idea here is that if I've described my sensor using AADL, I should be able to describe the various ways that it might fail. That way, when I compose my system, I can think about how that sensor failure might impact the overall system's ability to do its job. This research is actually already transitioning to practice. As you can see, we revised the error model and totally overhauled it in 2014. And now multiple contractors in the Joint Multi-Role Mission System Architecture Demonstration Program, or JMR-IMSAD, are using AADL in addition to the EMV2 Annex to describe various system components. And they're able to do this because this work was described in an annex to the core AADL language and supported via our open source tooling, OSATE. So they don't have to go out and read my paper, they don't have to go out and read Jerome's paper or the publication of any of our colleagues. They can get this knowledge just by downloading our tooling. As you can see, the safety work continues, and in the future we're going to be looking at increasingly autonomous systems and how we might model the various ways that things might go wrong so that we can think about how to make those systems safer too. Safety is only one line of research, though, that has been conducted using AADL. This is a more holistic view of the lines of research enabled by AADL. And it's not that AADL is key to, say, code generation research or behavior, but rather that AADL works with code generation technology. So if someone publishes a cool idea on code generation or requirement specification, or maybe resource budgeting and latency, that idea then can be embedded in AADL. The algorithms that are developed can be encoded in OSATE. And so then downloading this tool, OSATE, using AADL as a language, lets you get access to this research. And so we've seen a number of projects in DoD projects are shown here in blue, non-DoD projects in green, use various research ideas by using AADL and OSATE. So we've had users, of course, within the DoD that we're going to talk about more, but also groups like the European Space Agency, the Food and Drug Administration here in the US, a number of organizations that work with safety critical systems have found value in AADL's encoding of various research ideas. So let's talk a little bit more about that DoD impact. Specifically, I want to be sure and highlight the story of Army Aviation, because we have really had this tremendous partnership with the U.S. Army. If you were at the research review here at the SEI in 2019, you would have seen a presentation that I gave jointly with Alex Boydston, who works with the U.S. Army, and he talked about the benefits of AADL and ACVIP, or the architecture-centric virtual integration process, which really is the process by which we say this is a good way or the correct way to use AADL to specify components and virtually integrate them. It's that architecture-centric virtual integration that I mentioned early on in this presentation. So Alex and the Army have found that there are a number of benefits to AADL and the ACVIP process that let you find problems early, let you reduce risk, and also, like we studied in the IC project, increase cybersecurity, because there are fewer gaps in the understanding of a system than you might have if you write your requirements out using narrative English. So this is particularly important in things like aviation, or in domains like aviation, because certification plays such a huge role in getting these systems built and getting them fielded. And so certification authorities, of course, appreciate unambiguous statements. So these unambiguous statements in languages like AADL can support certification for airworthiness, safety, cybersecurity, and things like that. It's not just the Army that has found these benefits, though. One of the key research projects that we built on in IC was DARPA's HACMS project, or the High Assurance Cyber Military Systems. The idea here was that academic and industrial performers were asked to create an attack-resistant system. And Draper Labs was contracted as a red team to test just how attack-resistant these systems were. Collins' team used AADL and the research outputs of previous SEI research projects like that architecture-led system assurance, and created a system that Draper was unsuccessful at attacking. This is notable because every other system in the competition was successfully compromised. So AADL was not the only technology used, but it was sort of the architectural backbone that defined the components, gave them strict component definitions, these unambiguous statements of what was and was not intended to be in the system. And so there were fewer gaps then for the red team to exploit using their various techniques. AADL's use by both researchers and practitioners enables a really smooth transition pathway from research to practice. So you've likely heard of what's called the Valley of Death, which is the gap between academic research and industrial use. The idea that there are researchers like the Software Engineering Institute or Kansas State University, maybe Telecom Paris or Invenium Labs, that have cool ideas, and they describe these ideas using maybe mathematical statements or custom languages that a grad student whipped up and used for a couple of years. And then there are industrial users that have very concrete needs. They need problems solved. They're facing budget overruns in terms of time and in terms of cost. And so these users like the Army and Dassault have these concrete needs. But they're separated because a lot of times the research outputs are not directly usable by industry. So this is what we mean by the Valley of Death. AADL helps us bridge this valley because the researchers, in this case SEI, K-State, are using the same technology that the industrial practitioners are. So when I come up with something cool, when Jerome comes up with something cool, or a colleague here comes up with a neat idea, they can encode that in AADL, and that can be standardized and then used by practitioners. If a colleague at GTRI or at Invenium Labs comes up with a neat algorithm for model-based engineering, that can be encoded in OSATE and downloaded by the DoD and industry. We don't have to rely on someone finding our paper, understanding all the math in it and building their own implementation. Instead, they can just use our tools the way they have been using them and get access to the knowledge that we have embedded in there. So that's really AADL's tool as sort of this bridge from research to industry that makes it such a pivotal technology and a fun one as a researcher who likes seeing his work used to work with. So now we're going to look forward a little bit and talk about the digital engineering strategy. So as you may be aware, in June of 2018, the DoD published its digital engineering strategy, and Michael Griffin wrote that the document described what the goal was, but those implementing the practices had to develop the how, or the implementation steps necessary to apply digital engineering in each enterprise. What has happened in a lot of cases is that there are a series of digital models that provide an authoritative source of truth. So think CAD, or computer-aided drafting models, for design. They are authoritative and can be used in a formal development process. We think that AADL can be used for the safety-critical embedded systems as it is a model that supports integration, that virtual integration that I talked about earlier. It supports these formal development processes, and notably, like the second tenet in the graphic here on the right, it provides this authoritative source of truth. You can embed the knowledge that you have about your system at a given time using AADL properties, and those are unambiguous, and they can be shared with other system designers, with certification authorities, and the various types of entities that need to know various types of details about your system. We at the SEI are not the only ones that have had this recognition. Alex Boydston, that gentleman from the Army that I mentioned earlier, as well as Peter Filer, a scientist here at the SEI, and two scientists from Advenium Labs, published a document that said that the architecture-centric virtual integration process plays this key role in addressing problems with cyber-physical systems and can be this key contributor to the digital engineering strategy. So the takeaway that I hope to convey is that AADL is a tool that you can use whether you're on the more research or the more applied end of the system development spectrum. So if you want help, or if you have questions, or if you just want to learn more, please reach out. Thanks.
Hello, everyone. Welcome back again to our question, answer, and panel session. My name is again Ipek Özkaya, and I'm here with my colleagues, Sam Proctor and Jerome Hughes. So Sam, thanks a lot for the presentation. And during your presentation, there was a question that came in, which is, do you announce new embeds to downloads? So can you explain a little bit about our model of distribution?
Sure. So I'm going to interpret this question a little bit and yell at me in chat if this is not correct. But my understanding is that the question is really about, do we announce new sort of features or plugins to OSATE? And the answer to that is yes, but the sort of pipeline that moves from early research to late maturity sees different announcements of different features at different points. So if we come up with a totally new analysis or plugin, it doesn't ship with OSATE or the tool environment or even the language immediately. Instead, the language changes are circulated in the standardization committee, the AADL committee, and discussed, debated, and refined as part of that. Tooling is typically first published on some sort of experimental plugin website that you have to seek out and look for because those plugins aren't really ready for mainstream use. Accompanying that a lot of times is an academic publication that describes the intended use, related work, and any shortcomings that we hope to address. As early adopters, use that tool, give us feedback, use the language changes, give us feedback. Then we see we see sort of a maturation of it. And at some point, it will be pulled into the main OSATE release and announced as part of the changes that are included with every new release of the tool.
Yeah, and Patty clarified that the question was when new ideas, cool ideas are added to the AADL, and I think you exactly hit it right on. There's a process that is followed, and I think one of the strengths of the approach we have and the leadership position of the SEI is the community involvement, and it's vetted by the committee as well as standards committees before it becomes part of the overall bundle. Okay.
Absolutely. And I would just add to that, that if you're interested in this type of thing, we always need more participation in the AADL committee. If you see things that could be changed, the easiest time and the best time is of course early. So whether you're an industrial participant, someone from the DoD or from academia, we're really interested in your feedback on all sorts of different types of ideas. So please get involved.
So we have another question from Mr. Thomas from MITRE, and it goes, at MITRE, we have developed security safety simulation tools that integrate AADL and smooth models. We would like to reach out to you, right? So this is actually, we welcome that even to us, and let's chat afterwards. And we definitely always take on the community stuff and work with everybody that is interested. So at this point, I'd like to step back, and I'll start with you, Sam, but Jerome, please chime in. So architecting is all about trade-offs. And we talked before when we were talking with Jerome and James that there's not one model fits for all, and there are strengths and weaknesses of every single approach. But what quality attributes are best to model with AADL, and what are some of the ones that are actually excel, and are there any gaps that the community could fill in from that perspective?
Absolutely, absolutely. So some of the quality attributes that have received maybe the most attention are things like the end-to-end system latency. Certain notions of scheduling within a system have been studied pretty well, have seen some use by DoD and industrial partners. And as a result, the tooling is fairly mature for that. So if you want to investigate trade-offs regarding those sort of latencies or scheduling questions, AADL is a great tool. As I mentioned in the presentation, there's also a nearly 14-year history of modeling safety related problems or questions, things like off-nominal behavior. So using the error modeling annex, these types of questions can be answered, and the trade-offs of different things can be explored there. I would also mention that a lot of people do a very sort of manual form of trade-off analysis just by modeling their systems in AADL. And even before you dive into latency specification or safety specifications, just having a high fidelity specification of your components interface reveals a lot of system level issues that would typically present at integration time. And so you can get a lot of good trade-off analysis there. To get back to Patty's earlier question about, where are new things announced, one of the more researchy, not ready for prime time, but very cool ideas is an automated trade space analysis tool called GATSI, or the Guided Architecture Trade Space Explorer. And this was like I mentioned, was all about the automated exploration of trade space, and used any of the plugins that come with OSATE to compare different architectures. So trade space is definitely something close to our heart, whether you're doing that manually or you want some more high-tech automated type program.
All right. And anything to add, Jerome, to that list?
Yeah, probably just also to echo some of the questions I see on the chat. So with the SEI, we are leading the technical writing of the AADL standard documents. So we have meeting quarterly. So if you want to learn more about the process, to be involved, reach out to us. We'll be very happy to tell you more about that. Especially I see the question for Mr. Thomas about this integration of Simulink and AADL. For sure, we are interested to learn more, because if it can improve the language, we'll be really interested into incorporating that. We got subsequent questions also about the adoption of AADL. So yes, probably we can mention live that I see Rob mentioned that also on the chat, that we'll be having DoD-focused event early February that will be live, similar setting as this SEI Research Review, on the usage of AADL and AGVIP that Sam presented in the context of DoD programs, especially the Future Vertical Lift series of helicopters. What we can report is that we are still transitioning the technology, increasing the scale of TRL with a major avionics company. That for sure is a hot topic that will keep us busy for 2021 and probably for the following years.
So thanks a lot for that, Jerome. And there are a couple of questions, like, for example, what are some of the defense contractors like Boeing, Lockheed, and Northrop Grumman are doing? I think the best way to learn these actually is to attend our AADL User Day, which is upcoming on 3rd and 4th of February, 2021. Sign up to our mailing list or reach out to us, and we'll definitely make sure that everybody that is interested in learn more and, more importantly, interact with the early adopters more, will be more than happy to connect and make sure that the information is shared. So I'll go to the next question from Ray. And Ray says, many defense contractors are using models superficially, if at all. How do we encourage the adoption of model-based techniques? Excellent question. So Jerome, Sam, would like to get started?
I can start on
Jerome,
this
go
one.
for it.
I mean, I've been involved in AADL since 2006, so it was a very long time ago. And actually, I've been on both sides of the Atlantic. For many, many years, I worked with the European Space Agency into transitioning AADL into one big project that is called TASTE, which is for the automated code generation from high-level models that is using AADL internally for some representations. What we have learned through this exercise is that you encourage adoption by advocacy again and again and again. And actually, it is something that happened in the mid-90s when SCADE emerged as a solution for auto-coding, again, in the avionics domain. So first, we have to do advocacy. Second, we have to build metrics to demonstrate any potentialities for return on investment. And again, there is a team working on that internal to the SEI on very specific customer project to demonstrate the return on investment. And we also have a technical report that has been published, I think, in 2018, made as part of the SAVI working group, System Architecture Virtual Integration working group as part of the AVSI consortium that demonstrated some of the potentialities for return of investment on large programs that enabled, that informed a US Army decision to push forward AADL even further for the next coming years.
Sam, anything to add?
No, I would just sort of echo that we have also seen the use of models superficially. It's something that we're working on, what is the best advocacy strategy? So definitely sympathize with that experience.
And I think it's a combination of challenges. One, whether the models are high fidelity enough to be able to address some of the complex challenges we have. There's that as their fidelity and capabilities increase, I think adoption challenges decrease as well. There's education aspects, and there's of course the processes and the cultural barriers with the acquisition lifecycle. That is a whole different slew of expertise and changes that need to happen. I think part of the getting ahead of the curve is to be able to really work parallel while we're maturing technology. We also set the right acquisition pathways and adoption strategies and learning aspects. So that's probably our best answer. We're trying to do our part with these user days as well as courses, putting our technical material openly out there, but also welcome sharing experiences. And I think we can all learn from it. So with that, I will actually go to the next question, which is kind of related, because the reality of the DoD software is legacy. We have a lot of legacy software, not all of which, most of which is not developed with model-based software engineering approaches, let alone AADL. So what is the role of OSAT in AADL to play when you have a legacy system and that was not used, developed using these approaches? Is there an entry, or what might be some of the steps that an organization can take? Jerome,
I may take that one, Ipek, if you want. The first question is, what is the objective of the modeling exercise? So in the past, we already made some investigation on that. And I think Sam mentioned the Apache example, where it was a question of modernizing an existing system and for that do some trade-off analysis. If your objective through the modeling exercise is to get some insights about what is the trade space for redesigning a system, then you have to just realize that your modeling exercise is simply take the current system, do an abstraction, do some analysis, make an informed decision, and go back to traditional legacy software modernization. And this path is as effective as starting from scratch with a model and do the full cycle. It's really a question of having some flexibility, flexible mindset, so as to accept that a model is simply an intermediate step in a larger system engineering process. And with that, you can find a spot for AADL in many, many different settings.
Mm-hmm. Right. Anything
Yeah.
to add?
I would add to that really you're modeling, whether you are modeling in sort of a greenfield type development or something more legacy related, your modeling should be driven by your objectives. So if you are having an issue that you suspect comes from jittery latency or something like that, then your model should be driven by that. And in that regard, sort of there is very little difference between modeling a system that doesn't exist and one that does, because really what you're doing is you're only modeling a portion of your system. You're modeling enough of it to get the sort of answers that you're looking for. We don't often recommend that people just model a system entirely in AADL for the sake of completeness, rather that your model should only extend far enough to get you the answers that you're looking for.
Yeah, and I think you bring up a very important point. What is the answer you're trying to get to, and how, what level of specificity? I myself have been involved in some of the exercises where latency was an issue. There were multiple organizations involved, and by being able to model that particular portion end to end using AADL or a modeling approach, we were able to zoom in into where the problem might be, and then go back to the system and do the corrections. The corrections are easy often. It's really what is hard is to find where the failure is and what you would need to correct. And that's where I think these techniques can have a lot of power, even you're dealing with a system that may not necessarily be developed using some of these modern techniques from scratch. With that, maybe before we close, there were lots of questions in terms of what are some of the organizations adopting, what are their experiences. We see some superficiality in terms of using MBSE approaches. So if an organization would like to adopt these techniques, what are your recommendations? How should they get started in terms of embracing AADL and model-based software engineering?
I think that the sort of related to the answer to the previous question, really you need to go into it saying we're looking for X. We have had the best luck when we work with organizations that say, I have this problem, can AADL help us? If so, how? And in fact, some organizations have basically entirely on their own with sort of the publicly available materials about AADL taught themselves enough to get models up off the ground, analyze those models and got the answers that they're looking for, and then either said, okay, that's enough, or expanded from there. But I would say that it is generally the best choice to go into the modeling exercise with some specific outcome in mind, and then orienting everything, training, sort of the materials you use, the amount of time you spend on it, around that answer.
Jerome, any last closing thoughts to add?
Yeah, just probably to echo that, understand what is your process, understand where you feel that AADL might be an option, and see how you can integrate it. But I would say also training and continuous training is really important. Learning AADL is a process that requires a couple of hours. I've been through that with a couple of institutions recently, with Georgia Tech, for instance. But yeah, training is of paramount importance for yourself, for your team, just so that you understand how you can improve your practice. And what we have seen through 20 years of research with AADL is that there are multiple spots where we can do it, either very specific parts or as a whole with AgWeb. So we are really excited to work on that at the SEI.
And so thank you very much both. And as both of my colleagues mentioned, we have all these resources available. We have the Use AADL User Day coming up February 3-4, 2021. But I think the bottom line goes back to the more specific, your goals and objectives, especially your architectural significant requirements and what response measures you're trying to model, you'll get the most fidelity out of these techniques that we're showcasing. And there's definitely room to improve, but we've seen how well they can work when you actually can marry your goals with the available automation that is up and coming. With that, thank you both, and thank you all at the audience for streaming with us. I will close the panel, and next up will be our CTO Tom Langstaff to bring the day to a closure. Thank you all.
Thank you.
Thank you.
The SEI 2020 Research Review. Wow, what a great morning in terms of coming together all the different elements that we wanted to do for the introduction of the day of software and coming into place. You know, I went all the way through our first panel this morning, chaired by Anita Carlton, and really was trying hard to say, how could I take out some summary? How could I take out some elements of what was happening this morning so that I might be able to sum it up this afternoon? And I've got to tell you, if you didn't see the panel, I'm just going to have to suggest you go back and watch the panel, because there was just so many rich elements from all these different perspectives that came around that it made it really hard to summarize. I do have a couple of individual statements I'm just going to say to whet your appetite and to sort of put them in place there. So Deb Frinke basically really talked about big data and big science that's coming into that. And one of the things that she really talked about was big science is ever more dependent upon some of the original software techniques like version control and coming into that. And that there were lots of data engineering that was going to be absolutely essential in the moving forward of what we wanted to do with regard to big science. And this resonates really well to what we're doing these days in terms of making scientific advance through the use of software, through the use of data science, and through the use of really new innovative techniques in AI. So I thought that was just really perfect coming into that place. Michael McQuaid, following after that, really talking about what's one of the most important things, making sure we educate decision makers. Because no matter how good our software, our AI, our various future is going to be in this area, if the decision makers don't know how to set the appropriate policy based on this, then it's never going to be as effective as a tool for DoD, as a tool for industry, as a tool for what we're going to be using going forward. So this whole idea about educating decision makers and creating a realistic view of what AI can do, what it can't do, what the real promise is of sort of where we're going. And then Vint Cerf, who certainly has that long-term perspective of everything that's been going on in this business since the very beginning of the internet and coming in that way. And really, I love the statement he said, let's separate vision versus hallucination. And let's really get into what it is that can happen for real and what we do versus what really is out of the realm of possibility and things that are going to happen there. His concept that he brought up of minimal viable product is one that I think has been very valuable over the course of the entire history of Agile and DevOps and coming into that area. And it points out that it's beyond just a process of software development, that minimum viable product is a concept that really applies to all complex systems and all of the incremental development of systems that we're going to be using in future years and coming in that way. So then we had Al Danek, which I'm really happy that he got to step in for today, really talking about how do you make explicit the intent of the software, not just the requirements, not just the functional capability, but in a dynamic environment, how do you reflect the intent of what's moving forward with that? And I thought that was a really key insight into the way that the future of software has to develop. Sarah Manning-Dawson then comes in and talks about sort of the data being the center of everything. And I got to tell you, that really resonated with me because the more I think about what it is that makes software special, I keep coming back to data in all of its forms. The data that's stored long-term in the cloud, the data in motion that's coming across our network, the data in flight as it's inside the software being manipulated. So all of this has become key to really understanding how to create the future of software engineering and come into that way. Bill Shirless, of course, as one of our national treasures at DARPA, really trying to understand where the future is going to be in terms of coming into this, basically making the point that remember that software is a creative process and that no matter how much automation and how much basic use of AI that we're going to do to help the programmer, there's going to be a nature of innovation and creativity that we always have to apply to software. So the idea that someday we're going to sit back and software is just going to create itself without the creativity of humans being involved is really out of the realm of possibility for what we're seeing right now. That creative spark that comes in from all of us that are working with software is key no matter how advanced our AI is going to get in this area. And finally, so when we talked with Michael, sorry, I'm going to get his name, Michael Donnie comes in, basically talking about when you think about AI, there is a whole lot between now and general AI that's going to be valuable coming into place. And the idea that the Jake is going to be applying some of the techniques that we use within AI long in advance of when we get general AI that kind of comes into this, and sort of AI in the science fiction sense is really, there's a huge amount of benefit that we're going to get way before then. So I stepped back and I sort of looked across all of these comments and I said, how did that frame today? That really kind of framed today in a way of thinking about architecture, modeling, and workforce. Those areas that we come in where everything is structured around an aligned architecture and everything basically begins to move to the right abstraction. Vince Cerf actually mentioned abstraction layers as well during the panel. The right layers of abstraction in modeling, and finally the use of education, training, and the development of our workforce to do all of this were common themes that ran through all of these techniques that went through. And that, I thought, was a beautiful lead-in to the presentations this afternoon, starting with James Ivers, really, who I think had one of my favorite phrases of the day, which is, change is the real constant. So when you think about that, I just love the idea that the constant thing that we're going to have going forward is that nothing is going to be constant, is that everything is going to change. And that we have to have dynamic systems and adaptive systems, not because there's a short-term need for it, because long-term that is what our software environments are going to look like. Then sort of coming into the Jerome Ooze, where really we talked about the remarkable advances that we can get by doing some of the combination of model-based software engineering, of TwinOps, of DevOps, and really bringing all those things together to create sort of a cyber physics system, not just a cyber physical system that we've been dealing with IoT and areas like that for a long time, but systems that bring cyber and the natural laws of physics together within the future of systems. And the use of all of these technologies to begin to adapt these kinds of rules, one from the continuous universe and one for the digital universe, is going to transform the nature of what we expect software to do and what we expect software to contribute in the future. And then, of course, we came into Sam Proctor's presentation toward the end, really talking about how, all these things are really great, but when it comes down to it, tooling on existing things like OSATE and AADL are what really gives us the capability to move forward, really gives us that ability to apply these techniques to real software. And I love the questions that came back in. How do we know where to find these things? When are they going to be announced? Where are they going to be announced? This tells me that you get it. You know that out there the important things are the tooling that's going to be available for DoD and for the private sector and for the world to be able to take these techniques and really move them forward. And coming into the end with Sam, really talking about that bridge between research to industry. And I talked a little bit last week, earlier this week, about the people as being the quality of what happens at the SEI. And one of the really special things about the SEI is that the researchers that we have here really care that the work actually gets out into practice and gets out into DoD and really kind of moves into that area. And that just makes it kind of a special place. So with that in mind, what I want to do is encourage you at this point, right after I finish, to move from here into the poster sessions. If you've registered for the forum this week, you will have the links to the Zoom sessions. And unlike the YouTube you've been watching and unlike the things where you type in your text chats, which are great, you'll be able to turn on your video and your microphone and really interact and talk over the posters and talk about what's going on. We have 4 concurrent posters happening right after this. High assurance software-defined IoT security, investigating the feasibility of an integrated causal model for software cost control, multi-core confidence, and rapid certification of trust. If any of those strike your fancy, I strongly encourage you to go out, talk to the PIs that are there, look at the posters, and really reflect your comments and your capabilities against what you see in the poster session. We try to make this as interactive as we possibly can. Thank you for the questions that have come in on chat today. Again, they've been just excellent and driving us in the right place. If you have more questions and more comments and you want to get in touch with us, you can. Just send email to info@sei.cmu.edu. Say in there who it is you want to talk to, what your questions are. We will make sure they get routed to the right place and that you get an answer back. So Tomorrow is our 4th day of the research review, and I hope you'll come back. Tomorrow's themes are going to be around CI/CD, acquisition, sustainment, more about the workforce. So we're going to take all the things that we've been doing here and begin to really bring them together with regard to how do we use this within the process of modern software engineering and move that forward. So I hope that I will see you all tomorrow. We will wrap up at the end of the day. No poster sessions tomorrow, so today is your opportunity to get into the poster session. Tomorrow, come on back, and we will hopefully pick up and give you more information that you can take off and use. With that, I thank you very much for being here. I look forward to seeing some of you inside the poster sessions. Bye-bye.